How's it going, everybody? How's it going? What's up? We are 12 days into STREAMMAS. Wow, that has gone so fast, hey? It doesn't feel like I've done 12 streams already. What the hell have I done 12 streams about? I have to look back through my thing. I can't even remember. Like 12 seems like a pretty large number of streams. Can't even remember what I did them on now. But yes, we're halfway there. Hence the title of this video. We only have 12 more streams to go. This is number 12, and then we have 12 more streams until December the 24th, which will be the last one. I imagine December 24th will be a fun one. I'd probably, I don't know, I might not do any repairs on the 24th one. Depends on what you guys think, really, what you guys fancy. But we could just do some funny stuff on the 24th one, some festive stuff, festive games, amplifier repair games or something. I don't know, I'll come up with something funny. But yes, halfway there, gentlemen. How's it going? 11 streams. This is number 12, right? Surely. This is number... Oh, okay. Okay, fine. Very, very clever, Elliot. Yes, there was only 11 streams because one of the streams was actually not a stream. It was me being stuck in my car. Yes, okay, fine. You're right. This has been 11. This is stream number 11, but day number 12. So, now this evening... For those of you that were here with me last night, you'll know that we had more headaches with the Hertz amplifier, but I don't think I'm going to spend too much time on that this evening. I think we're going to move on and do some other kind of interesting stuff, look at some other interesting amplifiers, and just sort of crack on and what the hell was that for? Leave the Hertz stuff for another time. But just before we do that, there was a couple of tests that I wanted to do before we move on. While I still have it on my bench here, make sure all my cameras work. I haven't actually flicked through my cameras yet. Make sure they're all working this evening. Yep, that one's good. Hat cam is good. This one's good. I just need to go and open MIDI to key to get my other buttons working. Start, and then I get my scope screen. Yeah, there we go. Okay. So, what was I saying? Yes, a couple more tests that I want to do on the Hertz just before we move on to the next one. I have ordered a few parts. I've ordered some new operational amplifiers. I also have pulled 4 TL084 CNs from a donor board, which I've checked are pretty much the same as a 074 CN. So, we're going to just test with those this evening. Just a couple of quick tests. Now, following on from last night, the things that I've got in my head surrounding this amplifier are follows. One, it could be a test bench issue. It could be the fact that the amplifier doesn't like the ground reference or the grounding sort of pathway between its main ground in the power battery section and the output ground on the RCAs. Obviously they're linked. I've got my power supply just up here, and that shares a ground with my signal generator just under here. And between those two grounds with the long RCA cable, there's 46 ohms between them. So it might not like that. It might want a floating ground. So for a test this evening, I have my SPL Dynamics Next LCD unit, which is a completely floating unit. It's battery powered. I've just got it plugged in and charging actually to a little Anchor battery charger down here. So this is completely floating now from the power supply of the amplifier. So the ground is isolated, and this is a separate device. So we're going to use that and see whether that makes any difference to the amplifier, killing the operational amplifiers. Additionally, another thing that I've got that we're going to do is I've installed some headers just to make things a little easier onto here so we can drop in and out these op amps. One thing that I was actually wondering was, is it not killing the op amps? Maybe some voltage is just leaking through a capacitor or resistor or something on the board, and it looks like it kills the op amp. But then by removing the op amp, we remove the, we sort of discharge the leak or something like that. So I've got all the op amps that we pulled out from the boards like yesterday and the day before. Got them all still on the bench here. So we're gonna sort of plug these in to the headers in and out and see which ones are leaking voltage, see if it's actually killing them or not without keep soldering and desoldering all the time. So that's another test I wanted to do. Furthermore, I also want to test that we don't have any spikes on the VCC lines. Now, myself, like a couple of guys on my Discord channel, very, very knowledgeable guys, actually helped me out throughout the course of last night after the stream and today. We looked up, someone found a schematic for this amplifier, which is fantastic, and we were able to kind of work out that, to be honest, really, there's nothing that would kill both of these op amps, like one randomly and one the other. There's nothing that's common to both of them other than the VCC, really. So if anything's going to be killing these, it's likely to be a spike on VCC or a dropout of one of the VCCs. So what we're going to do first is I've got my oscilloscope here on rolling mode. Rolling mode is a bit like a heart rate monitor. It just rolls and rolls and rolls. So basically any sort of pulses or spikes or anything on the scope screen here they're displayed instantly, and then they stay on the screen so we can see that an event occurred. Like this, you see how I'm just touching my probes here, and you can see that an event occurred. So what I'm going to do is I'm going to put these on the VCC pins of the op amps here, and we're going to just, while the amplifier is up and running for a bit, we're just going to monitor over the course of a few minutes to see whether we see any sort of variance or drops or dips or anything. So guys, pay close attention to the scope screen in a minute. We're going to do that. I'm also going to keep an eye on it as I'm going up and down with the voltage up here on the power supply, just to see if it varies. It shouldn't do, because this is a 12 volt regulator, so it shouldn't vary at all. So yeah, that's probably the first test. Yeah, rest in peace, floor op amp. That sucked. And then after we've done that, we'll fit these donor board 084 ends, and we're going to test it with obviously the external frequency generator to see if it still dies with that. And then if it does still die using the external frequency generator, we're going to remove all RCA signals, put another 2 spare ones in, and see if it kills it without any signal as well, which will be interesting to find out. So let's start then. Let's start off this stream by just plugging in to the VCC pins here of the op amps, and let's monitor whilst we're reading some live chat, doing some Q&A, to keep an eye on the scope screen here to see if there's any variance between the VCC here as we turn on. So we've got 5 volts divide, so that means we should have 510 should be up about here. Let's get it on 12 volts. Let's just make sure there's nothing inside the amplifier. He's been sitting on my bench. I think we're good. Okay, cool. Let's power her up and see what we got. There we go. Okay. Now, interesting. Did you see that? Just as that came on there. That was interesting. Turn her off. So this is the VCC's down now. They kind of level shifted. Did you see that? They kind of came up to like here, and then they like level shifted, and that could just be I don't know, like the ground reference or something. I don't know. That was interesting. But the thing is that the op amps aren't being killed when the amps first turned on. The op amps are being killed while it's turned on. So something's obviously happening while it's turned on. Let's turn them on again. Let's have a look at what's going on. I'm going to slow down the scope a little bit so we get a slower roll. Ah, we get the 3 volts thing. That's see that right there. So when we apply the remote, we get like a little bump up to like the ground reference slightly changes on the output section until something activates, and then it goes back down again. That could just be to do with how my scope's grounded. So what I'm going to do is, now a lot of you guys often ask me, how do I ground my scope? My scope doesn't appear to be grounded in any way to the board as we're doing it now. The reason for that is because it's all grounded through the same ground as the output section. So what I'm going to do is, that's actually probably why we see that bump. So remember, the amplifier here, the main ground and the output section ground, they are coupled by a 1000 ohm resistor. So there's a 1000 ohms between the main ground and the output ground. They're not linked together. Okay, so that little bit of DC there, as we power the amplifier up, is obviously due to the slight potential difference between the grounds. So what I'm going to do is I'm going to float my scope. I'm going to lift my scope away from the power supply ground. I've got a big switch on the side just here. If I flick that, the scope is now floating and is not connected to the main ground. Now I'm going to connect my scope to the output side ground by clipping the crocodile clip here to the RCA ring There we go, and now it's grounded and has reference to the output section ground. So if I'm right, we now shouldn't get that little bump in DC really as we turn it on the VCC plus minus. Yep, there we go. So we just needed to change our ground reference ever so slightly. That's fine. Excellent stuff. So let's keep monitoring this, and let's look for spikes. So guys, I'm going to need your keen eyes. What do you reckon? Do you reckon a faster roll like this, or is that too fast? That's probably a good speed. I don't want to miss any spiky business here. So guys, keep an eye on this. This is obviously recording, so if I'm looking at the live chat and I miss something going on, then we can scroll back through the stream and see. Good evening, gentlemen. Yes, good stuff. We have 74 viewers just now. Cool. Jesse, evening. How's it going, everyone? So yes, have you guys got anything you'd like to ask? Should we do some Q&A while we're checking for spikes on here? Let's turn the voltage up to... yesterday, it died when we turned the voltage up to sort of like 14 volts here. It's a little bit noisy, perhaps, isn't it? Another thing which I'm curious to do is also, it died yesterday when I moved my oscilloscope probe over the amplifier. So if I just get a spare oscilloscope probe here, if I just kind of move it over the amp... No, I was just seeing if like it picked up any interference from the output section switching or anything like that, but it doesn't. What up, Sam? It's my 40th birthday today. Daniel, happy birthday. Jesus, that is a big one. Yeah, I'm about 10 years from that. It will come round fast, so I'm sure that at some point in the not too distant future we will be celebrating my 40th on stream. Yeah, dude, man, if I could back pay, if I could give you a super chat from here, then I would. Congratulations, man. Happy birthday to Daniel. Tell us what you did. What did you do today? I suppose it's difficult, really. You can't really do much during these times, but if you did anything exciting, let me know. So is 40 considered middle-aged then, hey? These waves, these VCCs, they look great actually. They don't look so bad. I'm gonna re-enable the VRMS. The thing is, with this scope, the way it works, it samples VRMS in little blocks. So it's nice and smooth rolling now, but if I enable the VRMS reading, you see it kind of like jolts as it reads VRMS. It kind of pauses ever so slightly, so I don't like that so much. I like it to be completely smooth, clean, like that. But yeah, as you can see here, we have if we do enable VRMS, we've got channel 1, channel 2 VRMS is exactly 12.04 volts on both. Literally, is absolutely identical. If I remove one, yep. So yeah, it's exactly the same. Exactly the same VCCs. Anthony, thank you for joining the stream again, my friend. Good to see you here. Going to the casino. Oh, wicked. Wicked stuff. Hope you win big. Have you ever serviced your HP scope before? I have the same model, but about 80% of the time it doesn't turn on. Seems like it's not booting, but it has power. No, I've never actually had to take the scope apart. I've had this scope for, what, freaking hell, like 6-7 years now. Used every day. Yeah, I haven't had to service it. It's never had any problems. It's just been straight reliable. Absolutely love it. Absolutely love it. Well, what a beast. Okay, so guys, I don't know about you, but I'm not seeing any fluctuations in this VCC. I'm going to crank the voltage up to 13.2 volts. See if that causes anything funky. Also, jiggle the board a little to cover your bases. Okay, not a bad idea. Let's give a few taps onto the board in a few places. I'm going to grab something non-conductive. Toothbrush will do well. Let's grab my things here. So just going to give the board a few sort of gentle taps in various places. I don't want to hit it too hard. obviously. That seems good. Seems good. Flexing 500 question on the DefBonce AAB. On the DefBonce AAB and Sundown SFB, they look almost identical inside, but the Sundown's last MOSFET is like 2 times the size of the others. What purpose does that serve? What the last MOSFET? I don't know if I've seen that. Do you mean that the output FETs are a different package to the other ones? But no, they are from the same circuit design. They're the same amplifier. The DefBonce and the Sundown SFB and the B2 Riot 16K, the Ground Zero version, they're all exactly the same circuit. They're the same amplifier. Try your signal generator from last night. Repeat the same situation. Put some input. Yeah, so there is actually some input going into the amplifier at the moment. Let's take our probe and let's have a look, see what signal we've got going in. We have the op amps obviously aren't present. I can't remember which pin it is that has the signal in it, but if I just turn my frequency generator up real quick, go up to about 50%. Let's try and see, where is our signal coming in? We have the RCA going into the bottom one. Now is it pin 1, 2, 3? Okay, I think that's our signal. Yep, there we go. There's our signal. So if we come off of roll, let's go on to main. You can see here, there's our signal. 55. What have we got? 50 hertz going in, and that's coming in on pin 3. I think it is. No, not pin 3, sorry. We have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pin 10 of the first 074 has the signal on it. Let's see if the signal is on any of these other pins here as well. Just out of interest. Or is it only the one? So only the one pin, only pin number, what was it, 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's only pin 10 has signal in it here. Just on this top 074. On the bottom one, is there any signal, or does it pass it on from the top one? Let's have a look. Nope. So the signal, the only signal is on this top one on pin 10. Cool. So, okay. Interesting. So we're not seeing any fluctuations in the VCC voltage, and we have signals. So I think the next thing to do then is, now that we've been measuring that for quite a while now, you would have thought that we'd have a spike or something. We'd see something if there was an issue with the VCC. So I think we should drop in a couple of these TL084CNs. I think we should drop a couple of those in, and I think that we should power the amp up and run it for a bit and see what happens now that we have our floating signal supply. Yo, still working on the hertz. Just to start with, we're just doing like a sort of little 15-20 minutes just of a few tests that I had in my head before we move on. I'm actually going to be looking at a B2 Audio Rage. I think this is the 2500. Yeah, a B2 Audio Rage 2500. Going to look at that in a little bit because that's a pretty cool little amplifier. Okay, so let's drop these into their headers, which I have now put into the board. Put it to useful, hey. So in one of these goes. Now these are donors, so they might have a little bit of solder still on some of their legs, so just going to have to give it a bit of a wiggle, a little bit of convincing. There we go, she is in. And the second one might take a bit more convincing because these are so close to each other that I think it might try and mount the other one. Oh, we're going to be tight. It is going to go in, but I think it's going to be tight. And obviously the headers don't really allow us to wiggle it around that much. Okay, no, that's good. I'm happy with that. There we go. So there's our new TL084CNs in the board right there. So now then, with our oscilloscope, we are going to... Now, where should I probe? There are a couple places I want to probe. The first place I want to probe is obviously going to be the output of this TL072C up here, because either that or the resistor here, because it's over here that we notice the DC. I think it's going to be this one here. There you go. This capacitor. This capacitor will have the DC on the signal if either of those op amps fail. So we're going to monitor the signal with our oscilloscope probe here on this DC blocking capacitor. Now the other one, the other oscilloscope, I've got 4 channels here to play with on my scope. Yeah, I've got 4 channels, so we can scope up, we can load up 4 different things on scope to read. And I like some suggestions, guys. What would you like to see? What should we probe? We can continue to probe the VCC if you like, 12 volts VCC, but I don't think that's going to fluctuate really. What else could we probe? We could probe the signal in. We could probe the signal into the first 084, perhaps, to see if that kind of like spikes or anything like that. Ah, here we go. Flexing 500. When you were on the B2 16K, you said they seem to pop if powered on with no load. Does that include if you're trying to set the game with no scope? Yes, absolutely. You must not power those amps up without a load connected across the outputs. Don't set those amplifiers. Look, those amplifiers have a clip light. Don't set them with a DD1. Why are you even considering setting your gains with a DD1 on an amplifier that has a built-in clip light? Guys, for your information, a built-in clip light on an amplifier is the most accurate form of clip detection that you can have, because it is a simple comparator that listens to the sine wave amplitude and compares it to the rail voltage. And as we know, when the sine wave reaches the rail voltage, that's clipping. So the light will come on when the sine wave touches the rail, which is exactly the point which it clips. So don't hook up your DD1 to your big amplifiers with clip lights. Not needed. The DD1 is only needed for amplifiers that don't have a built-in clip light. This comment makes no sense. Hello, Andrew. Apologies. I'm just going to shit on your comment right now. Half bridge is better than tar amps, and always and will always be this way unless tar amps release a half bridge. This is what really annoys me about how much misinformation is given by like manufacturers and just sort of people in the car audio scene. Full bridge has nothing to do with tar amps. Tar amps has nothing to do with full bridge. There are many amplifiers that you do not realize are full bridge, that are freaking excellent and old school and reliable. Check this out. Orion D2500 amplifier. Let's take a look at this one right here. Okay, look at this old school beast of an amplifier. Ah, yes, that, my friends, that is a full bridge amplifier. Now let's take a look at another one here. Let's go for JBL 14001. This, my friends, is one of the best, most reliable beastie car audio amplifiers in this power band between 1 to 2K. This benches 1950 watts RMS at 2 ohms and holds its own all the way down to 1.33 ohms, even 1 ohm if your rise is high enough, giving you about 2.5K. My friends, this is a full bridge amplifier. Let's move on. Alpine MRP 2000D, I think it is. Here we go. This is considered one of Alpine's best, most powerful Class D amplifiers of all time. This is a phenomenal circuit design, and this, if you take a look inside, actually uses the same circuit design as many Brazilians, and it is a full bridge amplifier. I could go on actually. There's a Hyphonics BXI 1600D. Here we go. This amplifier here uses a HIP 4080 chip on the outputs, which is a full bridge output section. So yeah, this amplifier is a full bridge amplifier. Many people rate these, some people don't. Vibe Monobox 4 also uses the HIP 4080 chip. This, my friends, is a full bridge amplifier. So stop comparing full bridge and tar amps to Korean half bridge amplifiers. Okay, there are Korean amplifiers that are typically half bridge because they're ancient old designs that will be reliable and stuff because they are a circuit that has been tweaked and had all the bugs ironed out over a long period of time. Brazilian amplifiers, because they're made on new modern circuit designs and modern circuit topology, they're utilizing full bridge technology, which why wouldn't they? Because it's the better thing to do for car amplifiers. But that's not to say that lots of other brands in the past have also utilized full bridge topology in their amplifiers because it makes more sense. Yeah, you can't strap them, but the full bridge topology is so much better. You can have so much more power density in a smaller package. You can use higher current, lower voltage MOSFETs. It's safer because there's lower rail voltages inside of the amplifier. It's just a better all-round solution. The problem that you're experiencing with Brazilian amplifiers, the thing that you have against Brazilian amplifiers is not that they're full bridge, it's just that they're Brazilian. Yeah, the Brazilian amplifiers are the way they are because they are made and they were designed in Brazil for the Brazilian market, not designed from the ground up for the American and Western and European markets. That's why they have less dynamic power. That's why they tend to clip a bit sooner. That's why they sound like they do with like less lows coming through, and like that's why you sometimes get some vocals come through your subs and stuff like that. It's nothing to do with the fact that they're full bridge. It's just because they're made in Brazil, not because they're full bridge. So stop saying full bridge versus, like, stop saying like Taramps full bridge amplifiers. Full bridge amplifiers aren't bad. Full bridge amplifiers aren't Brazilian. Okay, Brazilian amplifiers just happen to be mostly full bridge. Oh, for fuck's sake, my screen capture button was broken. I was tapping my screen capture button, but it's obviously come disconnected. These amplifiers here, let's give you the screen. Vibe Monobox 4, here we go. This one here. If you're in the UK, you may have experienced Vibe Monobox 4. Oh, fuck off. I don't care. Why has Google Images changed? Like, back in the day, you used to be able to click on an image and it would give you the big version of the image. Vibe Monobox 4, Orion 2500D. This one here, full bridge amplifier. Alpine MRP 2000D, full bridge amplifier. Hyphonics BXI 1600, full bridge amplifier. JBL GTO 14001, full bridge amplifier. There's so many that I could just go on and on and on. The ones that I see all the time, and I'm like, this is a full bridge, no worries. Okay. Yeah, Andrew, I'm sorry I went off on one a little bit then. It's not aimed at you whatsoever, but your comment just kind of ignited just annoyance really in my heart about how it seems to have been made an assumption that full bridge amplifiers are like Brazilians all the time, and like, you know, if an amplifier is full bridge, then I must be like a Brazilian. Well, that's not the case at all. You can have a full bridge amplifier designed like a Korean half bridge, just in full bridge topology, and it will be exactly the same. Yeah, a full bridge amplifier is just two Korean half bridges in strap kind of thing, you know, on the same PCB. But the thing is that the Brazilian circuit designs are really stripped back, and they're really basic and cheap designs and low filtering and full range nonsense and stuff. That's why the difference is there. So just so I understand the tech, if say an Sundown full bridge is 3K 1 ohm stable, isn't each half of that amp running at 0.5? Yes, absolutely. Each half of that amp is running at 0.5, but they're designed to. With a full bridge amplifier, okay, in order to create the same output sine wave voltage as a half bridge, you only need half the internal rail voltage, which means that you can double the current across the internal output section. So, you know, with higher voltage, lower current. With lower voltage, higher current. Generally, that's how things go. That's how components are generally rated. You know, it kind of equals itself out to a specific power level. If you've got 500 watts, yeah, you can either create 500 watts with a high voltage, low current, or you can create 500 watts with a low voltage, high current. So inside these full bridge amplifiers, you have lower voltages than in any half bridges, and each half of the bridge, or whatever, each separate side is running at half the impedance of the nominal load on the outputs, which is fine. They're designed to do that. Not a problem whatsoever. Yeah, if you were to point for, but again, it's the same though. Like, okay, let's take this amplifier for example. Okay, just so you understand how a lot of half bridge works. So this amplifier is a half bridge. Okay, and inside the amplifier, though, although it's a half bridge, we actually have two separate amplifiers, the same as a full bridge does. But the way that a full bridge works is it push-pulls on a speaker terminals like this. But the way that this amplifier works, we've got one amplifier here and one amplifier here. You see the two inductors? So this is one amplifier circuit. This half of the driver board, and this half here of the amplifier is one half. This is the other half. Now, instead of working together in push-pull, they actually work together. So these amplifiers are paralleled after the inductor. So when you wire this amplifier down to 1 ohm, each half of the amplifier is driving a 2 ohm load as far as it's concerned, because they parallel together after the inductors. So you have a 1 ohm load here, and it splits off, and this one sees 2 ohm and this one sees 2 ohm. But in a full bridge amplifier, it's the other way around. These two amplifiers would be in push-pull like this. Kind of in series, not really in series, but rather than being parallel together, they're working together in push-pull. So if you connect a 1 ohm load, each one will see 0.25 because they're kind of coming round into the other one like this. But in amplifiers, that's not a problem. That's not the reason. That is not the reason that you can't wire full bridge amps down lower than recommended 1 ohm impedance. There's nothing to do with that. It's just mainly because the Brazilian amplifiers that are utilizing full bridge topology, they are not they're not built ruggedly enough to cater for that additional current draw from the amp. They're pretty much on their limits already. They were designed for high inductance, high reactive load impedances from like big PA woofers and stuff in Brazil. That was the original design goal, was for these amplifiers to work on sort of the kind of sound systems they have in Brazil with PA drivers that rise quite high and, you know, full range stuff, not to drive these really inefficient, long, low frequency, long tones drawn out, a lot of current draw from the kind of subs we have in the West and in the States and Europe and stuff like that. So that's why now that Taramps and the other Brazilian brands, Sound Digital and stuff, now that they're exporting their amps to, you know, all the American market and the European market, that's why Taramps released the bass line, the bass series of amplifier. They released those because they were built up a bit stronger to cater for the way that they're used in America and stuff like that. Whereas the HD line were really made as kind of kick bass, mid-range, full-range amplifiers to run these ridiculous PA stacks that they have in their cars in Brazil. I'm just going to get my MIDI to key working again. MIDI key to key. Start. Now I should have my buttons working. Yay, buttons working again now. All right, so anyway, kind of went off the theme a little bit there. So let's crack on with this. So now we have our op amps in the board here. We have our signal generator hooked up. That's a floating device now, not connected to the main ground. We have our voltage here, going to start at a nice low voltage, about 10.7 volts on the power supply. Now we are probing with our oscilloscope. We're probing the signal, of course. And also, I guess we should be probing... What do people want to see? Do you want to see the VCC get probed? Plus minus 12 volts. Do you want to see that? Mike Honda, dude, thanks for the... holy crap, thanks for the 50. Sup, Bevis? I'm sorry, I'm going to miss today's live stream. Travel day. Having some nice time with my niece. Have a drink on me. Best luck with that shit that hurts. I'll check this out later. Dude, well, thanks very much for jumping in and letting me know. Don't worry about it, man. These streams, like I say, they'll be up and you can watch them anytime. Don't have to watch them now. You know, if you're busy, want to crack on with some other stuff, pay attention to it some other time, don't worry, man. That's absolutely fine. But, man, thank you so much for the 50. Absolute balling ass drop. From Mike Honda there. Massive respect. Thank you very much, my friend. Shoot me a message if you need anything. Mech for life. Is your car all right? Yeah, I believe so. Head gasket's fine. Engine seems fine. Just needs a new smaller belt and some sort of fluid flushes, and it should be ready to go. What about the Taramps MD line? I can't remember exactly why they released the MD line. Is the MD line full range as well? Maybe the MD line was a kind of slightly beefier full range. And the bass line was just a kind of subwoofer low frequency one. Now the outputs of the 12-volt regulators, the 12-volt regulators are just here. I just want somewhere to kind of clip my probes onto that's not too, you know, that's kind of easy to get to, if you know what I mean, with the probes. So let's have a look. I don't really want to clip it onto the op amps themselves. There's not enough room. I just want somewhere with enough room to clip the probes on it. I can probably shove one in here on this 7912. Now I just need to probe the 7812, but I also don't want to unclip it from the heatsink because I want it to stay nice and cool in there, you see. Maybe I can just get in there. Ah, there we go. Yep, just about got in there and just managed to clip that on to the output pin there. I think that's the output. I think pin 3 is the output for both of these, 7.8 and 7.9. Beavis, have you been repairing this for 3 days straight? Kind of, yeah. Okay, time to power up then. We're probing, let's turn all these channels on. So we've got, what have we got, 10 volts. I think I can't change that to, we've got 10 or 50. Well, let's turn the probe back, let's turn the probe down to ×1, actually. If we go ×1 on the probe, then I can actually probably choose 5 volts maybe? 0.5? No, 10. Oh, here we go. No, I can. There we go. 5 volts divide. 5 volts divide. Excellent. So, channel number 3. Channel number 3, we've got 5 volts divide on here. Channel number 2, we've got 5 volts divide. So we should see that rise up together. DC coupling, DC coupling. Channel number 1, we want the signal, the RCA signal. So we're probably going to go down to about 2 volts divide or maybe 1 volt divide to get zoomed in nicely on there. Want to reject high frequency? Yes. Okay, I think we're ready to power up and see. I'm just kind of worried about these probes sticking in here. I just want to make sure that they're not like shorting against the leg next to them or anything like that, because that would be the worst thing. I don't think they are. I guess we'll just power it up and see, hey? Yeah, there we go. So that came on fine. So I'm going to power it up fully now, and we're just going to monitor how it goes. We've got the sine wave here, current draw. Okay, relay clicks in. There we go. Okay, excellent stuff. So there is our sine wave and our VCC rails for the op amps. Okay, so let's crank the gain a little bit on the signal. And we should start to see some current draw from the amplifier. We're drawing 2.2. I've got the output of this amplifier hooked up to 16 ohms, a 16 ohm load. So nice and high, not too stressful for the amplifier. So you can see we've got 2.2, 2.3, there we go, 2.4. So yeah, we've got a little bit of signal going in there now. That's fine. I'm going to leave it at that. I'm just going to crank up one more, perhaps 2.5. There we go. So there's our signal. And remember, this isn't close to the rails. This is channel 1 is 1 volt divide. So if we go to the same, see this is the VCC rail, and this is how far away from the rail the signal is. In reality, I've just kind of zoomed in a bit on it. So we're going to leave this like that for a bit while we talk, and we're going to just hopefully pray that we don't get any DC start creeping in on that sine wave in the middle. Oh, the MD line is for mids and kick bass. That makes sense. MD, mid driver, perhaps. Yeah, is for mids and kick bass. Taramps have a speaker line called 7 driver. Oh, really? I've not seen any Taramp speakers myself. Sam, the most powerful strappable amplifier that you know. Okay, that would probably be the most powerful strappable amplifier that I know. I think that would probably be there's a big Korean half bridge by Vibe. It's the Vibe. Is it the Reaper? is it the... There's a Vibe audio amplifier in the UK here that's about 12k. Or actually, no, maybe the Digital Designs Z2C. That might be one of the most powerful strappable amps I've seen. That's like a kind of 10 or 12k. I think it might be a 12k. Very similar to the Vibe. And that is capable of, like, yeah, between 10 and 12k into 1 ohms. And obviously you can strap it for about 20, 24k. Black Death? No, not Black Death. That's the cheap shit. Apart from that, I'm trying to think if I know of any like big kind of 12 or 15Ks. All of the big sort of any amplifiers that are above 12K, they're all full bridge. Because once you get above sort of 10 to 12K, there aren't any MOSFETs. Okay, this is why you don't get these bigger amplifiers in half bridge, and the limit is about 10 or 12K. Okay, so with a half bridge amplifier, the rail voltages that are required to produce a sine wave. Okay, let's have a look just while we're doing this. Let's have a look at some of the requirements for the rails. So if we go to watts, let's have a look. Let's go to a watts ohms conversion calculator here. Let's also go to a RMS peak calculator. I think I've done one of these before. RMS voltage calculator. So I want a peak. I want a peak voltage calculator based on the RMS voltage. Here we go, peak voltage calculator, peak to peak. Oh no, I want peak to peak calculator. Peak to peak. Here we go, this is what I want. Right. What the fuck is this? What Walford? I'm pretty sure I haven't got an ad blocker on Firefox. So here we go. So let's take a look. Let's say that we want 10,000 watts RMS. No, let's do 12,000 watts RMS. Let's say we want 12,000 watts RMS and we want it into 1 ohm. Okay, so that means that we need a roughly 110 volt RMS sine wave. Okay, so 110 volt RMS sine wave. Enter the RMS to peak. So it should have 110 volt RMS. In that case, we will need a 311 volt peak to peak. No, that's not right. It's much higher than that, I think. Pretty sure it's much higher than that. I want All About Circuits website. I don't want this learning thing. Learning. I want this All About. So these are the good ones. Peak voltage calculator. I could just double the peak, couldn't I? Fuck it, I'll just double the peak. So if we enter our RMS voltage of 110. Ah, there we go. Oh, it's about the same. Okay, yeah, so it's about 310 volts peak to peak sine wave. So that means that the sine wave needs to fly up to 300. What is it? Peak to peak. No, it needs to fly up to 155 volts. And down, no, that's not right. 12,000 watts RMS, 1 ohm. Voltage, 109 volts RMS. That should be much more. Because I'm just thinking, so in all of the 12k amplifiers that I've seen, okay, the rail voltages are something like plus minus like 200 volts. Okay, so yeah, in the 12k amplifiers, when you have the voltage up at like 14 volts, where it's going to do its rated power, yeah, the rail voltages are up at, yeah, plus minus 200 volts, which means that the MOSFETs need to be rated for 500 volts, okay? Because if we see, obviously the MOSFETs, they switch rail to rail. So whatever your rail voltages are, plus minus 200 volts, there's 400 volts worth of potential difference between those, and the MOSFET needs a bit of headroom from the breakdown voltage. So for a amplifier that has 200 volts rail to rail, sorry, each rail is 200 volts, 400 volts rail to rail, you need MOSFET MOSFETs capable of 500 volts. Now, when you turn these amplifiers up to 16 volts or even like 18 volts, then you will see rail-to-rail voltages of around 500 volts, which is like really close to obviously these MOSFETs limits. Now, MOSFETs, you can get MOSFETs that are like 600 volts, 700 volts, but with a MOSFET, when you go that high on the MOSFET's voltage voltage you massively reduce the current capability. The MOSFETs don't really come in high currents from voltages that high. So in order to get in order to get power, what am I trying to say? So yeah, you're limited, pretty much. You're limited with amplifiers that are half bridge. You're limited to what MOSFETs are available without having to like load up the amplifier with like hundreds and hundreds of high voltage MOSFETs to get the current that you need. You're limited to about 500 volt parts. That's kind of the limit to where it starts getting ridiculous if you start going any higher. So for a half bridge amplifier, 500 volts MOSFETs is about the limit, which is about 12,000 watts RMS. When you're designing and building an amplifier, it ends up to be about 12,000 watts RMS. However, with full bridge, you only need half of the internal rail voltages to make the same power, because of push-pull. So now, if you change your design from half bridge to full bridge, you can swap out your 500 volt MOSFETs for 250 volt MOSFETs, which is why in the Korean full bridge amplifiers that we're seeing come out now, like the Vibe, the Edge, the DS18, etc. Those, and I think Wolfram do one as well. The MOSFETs in there are IOFP 4868 PBF, which are 250 volt. I think they might be 300 volt parts. So you can halve the rail voltage requirements. Therefore, you can get back decent current MOSFETs. MOSFETs that are able to pass high current, which is why these full bridge amplifiers are much smaller, because all of a sudden you've halved the voltage requirement from the MOSFETs, and therefore you can like double, you've got so much more current available to pass through the MOSFET, much lower RDS, so you need less of them, which is why the amps are smaller. So in order to have a half bridge amplifier that was strappable, that was any greater than 12K, you would need to be using IGBTs in the output section instead of MOSFETs. So you can go 600 volts, 800 volts, etc. on a half bridge output. And get the current there as well, because IGBTs are high voltage, high current parts. Yes, Snipex, that's where IGBTs come in. This is on the money. That's where they come in. But I haven't seen any half bridge amplifier designs using IGBTs. Guys, what the fuck is with this? The amplifier, there's no DC on the output yet, but we're still at 10 volts. Okay, let's crank the voltage up. What we got? 11, 12. Let's go up to 12.7 now. What happened to the amp? Did he find the culprit? So we are currently just testing. So we think the culprit might have been something to do with my test bench, in the way that it was sharing the output and the power supply grounds, potentially. But it's really weird because the amplifiers did come in with this issue. So I don't, the amplifiers did come in with dead op amps, so I'm a bit confused. But right now we are testing with a floating signal generator. So the signal generator is not connected to any of the bench power supply grounds whatsoever. It's just battery powered. So this is like a kind of floating head unit. So we are testing that, and we also have some TL084Ns in the board instead of the 74s. And so far we're good. So far we're good. Where can I buy a sweater like that? So because it is Christmas, because this is STREAMMAS, streaming Christmas. Every live stream I'm trying to wear a new terrible Christmas jumper. So this evening we're wearing this old blue one that I've had for years. It kind of has it doesn't actually have any Christmas kind of prints on it, but maybe that's a snowflake perhaps. But this is a very festive winter December jumper, isn't it? Or sweater as you guys call it. But I can't remember where I bought this from. Hi Sam, it snowed here yesterday. Tom, whereabouts are you located? Ah, snow. Jesus. The UK sucks with snow. Yeah, so, okay. So far, so good. 12.7 volts. So far, no DC. I would love to see Sam open one of those up sometime and see if they really are worth the cost. Oh, what the wait, what was that in reference to, James? Actually, B2 M15R is bridgeable. The M15R, what's that one? Oh, is that the big Raven? Yes, I think that might be the biggest one. That might be the biggest one. 30 kilowatts. Really? B2 M15. B2 M15R. That's the kind of 12K, isn't it? Let's have a look. Yes, yes. I've repaired one. I've repaired two of these. I have repaired two of these bad boys. These Ravens, absolute beasts. These things are freaking crazy, guys. If you want more of a kind of older school style circuit design, reliability, etc. But this amplifier contains all of the modern MOSFETs. This amplifier is an absolute monster. What an amplifier. What a beast. B2 really pulled it out of the bag with this one. This is a freaking beast. And yeah, this is half bridge. So yeah, this is strappable. What is the power rating of this? Just the official power rating here. We have power at 1 ohm, 14 volts. Yeah, it's 12K again. There we go. There's our limit. 12K limit. I'm not counting obviously with 16 volts. It claims it can do the 15K. Actually, that doesn't quite. I don't think that quite adds up with the square law correction factor for wattage, does it? Hang on a minute. Really? So if we take 14.4 divided by 16. Oh no, that's the wrong way around. We want to take 16 divided by 14.4. And then we want to square that, giving us our correction factor. Oh, for fuck's sake. Urgh! I hate the calculator on Windows. It's so counterintuitive. Right, 16 divided by 14.4 equals, square the result, and then times that by 11,500. Does that give us 15K? It's about 900 watts off. So I think the 15K either the 15K is slightly optimistic or the 11,500 is slightly underrated, because this is pretty accurate. This square law correction factor for input voltage versus output power is very accurate, because all it is just referencing the increase in rail voltage with the as the voltage of your power supply comes up, the rail voltage increases like that. So they start off at 0, and then this is your power supply voltage, this is your rail voltage. They go up like this, kind of thing. Like it's like there's a ratio kind of thing. It's square law correction factor. It's very accurate. Wait, actually, was I giving you the screen there? Yeah, well, I was giving you the screen. Could you see that? 16 divided by 14.4, square the result, times by 11,500. That's the kind of realistic power that we're going to get going from 14.4 to 16 volts. Yeah, but they're a freaking beast, and but that is pretty much the limit of a half bridge amplifier using MOSFETs. We'd have to be using IGBTs otherwise. Hey Sam, does the amp ever see what its hippopotamus? Hey Sam, does the amp ever see its wired ohm load? Sometimes, if the subwoofer if you're playing at tuning frequency, if you're playing at box tuning frequency, then it might see quite close to the nominal load. If the cone is being held very still. So you'll notice that if you play your subwoofer at tuning frequency, when the port is moving the most air, your subwoofer is staying very still in a lot of cases. If you are running a low motor force subwoofer, like a cheaper, like I don't know, Sony X-Plod, for example, is a good example. It's a good subwoofer, but it's a low motor force, large coil gap subwoofer. So with a Sony X-Plod, if you put it in a box and you play at box tuning frequency, in a ported box, port tuning frequency 33 Hertz, the cone of that cone of that Sony X-Plod will barely move, but there'll be a lot of displacement out of the port. That's how ported boxes work. They take the kinetic energy of the sub and they turn it into just air movement out of the port. They eat up all that energy from the cone, so they load the cone still. Now when the cone is still, it's not a coil moving in a magnet anymore as much, so the impedance rise is much less. impedance rise is greatest when the subwoofer is free air, because there's no load. It's just flapping around for all day long, so there's no resistance. The more you try and this is hard to do. The more you try and hold that cone still, the lower the impedance rise gets, and the closer to nominal you get. So yeah, only if you're playing like bad subwoofers at tuning frequency will you see quite close to your nominal impedance. Right, guys, we're still no DC. Let's crank it up to 14 volts now. I fucking hate 14 volts. I don't like it. I don't like it. Let's just check with the thermal imager, make sure nothing is getting funky in here. But we have the amplifier in a safe environment. The amplifier is loaded on the outputs. We have RCA signal going in. The amplifier is, is operating as it would do in a car, with a constant sine wave. So there shouldn't be any reason for this to explode. What do we have in the board here? We have the drive circuit. Yeah, the drive circuit's run fucking hot. Jesus Christ. The drive ICs are running at 70 degrees, and that's actually pretty normal in these. This is why a lot of the times you'll see these amps have fans like above the drive circuit, or they sometimes have heat sinks on the drive ICs. But yeah, this is in an open case environment in the workshop. Now put the back on this amplifier, suffocate it more with air, and then put this in the back of a hot car on a hot summer's day. Those chips, they'll be running at like over 100 degrees, no doubt about it. But that's normal. That is standard procedure here. Damn, 78 degrees. It could also be because these FETs actually that I'm using here, these are actually slightly harder to drive than the original ones. So it could be that it's actually working the drivers harder than normal. I might look into that. I might actually put some easier to drive FETs in there, because that is pretty darn hot, 74 degrees on the open case there. But what I'm most interested in, the reason I got this out, I just want to check out the heat on the op amps. What do we have? 28 degrees. So that 30 degrees, yeah, there's 30 degrees there now. So that is very similar to what we saw on the 074s. But you know what? The fact that this is still working, I think that this, then, gentlemen, is perhaps something that my workbench was doing to the op amps. Could those op amps be susceptible to failure from being heated by the hot air station? That is a possibility. However, the last set of op amps that we fitted into the amplifier weren't heated by the hot air station. They were soldered in from the bottom of the board normally. So that kind of debunks that theory slightly. I'm going to increase the signal level slightly. I want a fourth probe, really. If I can just get maybe a fourth probe out. I just want to read the... I don't want to remove my probes from any of the positions that they're in, because it's all very high voltage and stuff at the moment. So I'm just going to grab a fourth probe. I just want to read the output voltage on the speaker terminal. Just want to see how close to clipping we are with this amount of signal going in. Let's plug my fourth probe in there. Turn channel 4 on. Channel 4 we have, what is this probe? Is this a 10 volts? Yeah, 10 times. So we're going to go 10 times, and we want, oh, we've only got 1 or 5 volt divide. Oh, that sucks. Okay, that's freaking annoying, isn't it? Do I have another 100 volt probe, another times 100 probe in here? No, I don't think I do. I think these are all just times 10. That's really annoying. Can't really tell how close to clipping I am. Again, we're way off clipping, obviously, looking at this, because this is the output. So the output voltage is only what, like, I don't know, freaking a few volts. So let's increase the gain slightly here. 2.8, 2.9. Okay, that's not very much signal, is it? If we lower the frequency, will that help? Maybe the low pass, lower the frequency a touch. Ooh. 3 amps. We're down at, what are we down at now? 30 hertz. So the amplifier is running very, very easy. There's not very much voltage on the speaker terminals. This is with the signal generator here at 100%, so I can't turn it up any more than that. Maybe I should give it some more signal. Yeah, I'm going to give it some more signal. I'm going to get the amplifier playing a little bit harder. I'm going to turn the gain up a touch because the only difference now then, I guess, is that we have much less signal than we did last night. Much less signal amplitude. So I'm going to just turn the signal up, turn the gain up a touch on the amplifier to get some more signal coming in here. Well, voltage is your tone generator. The tone generator is quite weak on this. The tone generator at full volume only outputs. Let's go for voltage VRMS on source 4. VRMS. Yeah, it's only 1 volt divide. Oh, I need a ground reference for the RCA. One sec. Looks like there's a bit of DC on that actually. It's only 1.7. So 1.7 volt RMS is the output of the signal generator. So not particularly high. Looks like there's a bit of DC on that actually. If I stop that, function stop. Yeah, what the fuck? There's like 0.6 volts of DC. I mean, it doesn't matter so much because, you know, the amplifier blocks DC obviously, but that's not ideal. Weird. Never noticed that before. But that doesn't seem to matter. Right, so we're going to turn the gain up a touch now, get the gain a little bit higher to get the amplifier working a bit more, get a bit more signal into here. Let's flip her over carefully because we've got probes attached. And gain knob is this one. This one was on 0, so we're going to turn the gain actually up to about halfway now. So the gain's up at about halfway. And I'm going to turn the signal level right down on the function generator down to 10% output. Just to start with, I'm going to crank her up slowly. Okay, let's power her up again. Let's see. Okay, now let's start increasing the signal. 2.3 amps worth of current draw. 2.4, 2.6, 2.8, 3.2, 3.5, 4.1. We're at 80% output, 4.9. Now I can't see the top of the sine wave. I don't think I'll be able to either. So I don't know if we're clipping or not because I can't see the top of the sine wave we've probed on before because it doesn't go high enough. But we're only drawing 4.9 amps from the supply, so I doubt that that's an issue. I doubt that we're near clipping point, but the amplifier is just running a little bit harder now, that's all. When you probe your amplifier with an oscilloscope to set gains, aren't you changing the impedance, therefore affecting the measurement Wait, how would you be? Why would you be changing the impedance? The oscilloscope, obviously any test equipment, any equipment like multimeter, oscilloscope, clamp meter, any test equipment needs to not influence the circuit that you're testing, because otherwise that would completely nullify all of your readings. So test equipment is specifically designed to basically present an infinite resistance to the circuit that you're testing. So yeah, by probing your amplifier with your oscilloscope, you're not changing the impedance whatsoever. It's pretty much infinite impedance. It's so high that circuits just don't see it as a load. So no. Yeah, guys, you know what? I think this is fine. I think it must. What we now? We're an hour into the live stream, so this amp's been running for quite some time now. I think we're fine. I think we made it. I think we made it. Adam Francis, brother, I made it. What we got on? Jesse, I'm in northern Canada, and this time of year we're normally just loaded with snow, but not this year. Snows a bit and then goes bye-bye. Yeah, Canada. I really want to visit Canada at some point in the future. Adam Francis, how's it going, man? Yeah, so the amplifier, the idea with the Hertz was just to run one test, or one or two tests, and then move on to something else, because I think that we fixed it. I think the issue was actually my signal generator. I don't think this amplifier likes having a common ground on the output compared to its input ground. I think it needs to have a floating ground, which is very important to know for the customer. So yeah, interesting one. On this one, you can't do that trick on the back of the head unit where you ground the RCAs to the head unit case, because that's gonna cause this amplifier to kill its buffers here. Yep, I'm not seeing any DC here. Are you? I'm not seeing any DC. So I think that's fine. I think that's fixed. Awesome stuff. So let's move on to the next amplifier then. Let's finally move on from these Hertz amplifiers. We have done lots and lots of trial and error testing on these. So hopefully all of the stuff that I've been doing on these Hertz amplifiers has been somewhat useful to you in terms of, just expanding your knowledge a little bit with things that can happen and things that can go wrong, and how to fully test these amps, and just, I don't know, just hopefully it's been useful to you watching this issue unfold. I'm just going to put all of the Hertz parts back in these bags, ready for reassembly later. I'm going to put these back together after the live stream. Now, the amplifier that we're going to be looking at then is a B2 Rage amplifier. Really cool little thing. We're gonna go through what that amplifier consists of, and then we're going to find out what's wrong with it. Let's put all of these Hertz parts back in here. Yep, there we go. Back in here you go. In the bag. In the bag, nice and safe. Don't want you disappearing now, do we? I'd quite like to get one of those magnetic parts trays you can get. They're pretty cool. I just need to reconnect my scope to the main ground like that. You see how that disappears? Burp, burp. There we go. Let's pop the signal generator down there. Any more screws for the Hertz around here? I'm going to shove that in there. Any more Hertz parts? Don't think so. These are all the dead op amps from before. Okay, I think that's all of the Hertz parts. Shove that in there. Toothbrush. Don't forget to do your teeth, guys. Okay. Bye bye, Mr. Hertz. Let's unclip all of these oscilloscope probes from you, shall we? There we go, that's better, isn't it? You've been discharged from the hospital, sir. How much do you charge for these amplifier repairs? Right, so with this one, okay, obviously we all know how long this one has kind of taken to get to this point. However, what caused it to take this long wasn't really like, you know, it wasn't really because the amplifier repair was so long. What caused it to take this long was just the amount of time needed to figure out that perhaps my test bench was, you know, causing issues with it. So all of the time figuring that out, you know, I can't really charge the customer for that. So in terms of this amplifier repair, at the end of the day, just going back to basics, this amplifier needed 2 new 074Cs. I think that was all that this one needed. So, you know, I can't really charge a huge amount for that. The other one needed 2 new 074Cs, and it needs a shift register shifter, whatever it's called. So that one will be a little bit more. Now, obviously, we're not just going to charge for the parts, because it takes, you know, we're charging for parts a bit of time, and also we're charging for the experience, you know, and the knowledge required to do this stuff. So usually my repairs are charged based on parts, amount of time taken, and complexity of the repair. I actually have done a couple of amplifier repairs where the part cost absolutely nothing, like 10 pence. The time taken was about 10 minutes, but I will charge, I don't know, I might charge like between 80 and 120 pounds for that repair, because the knowledge of and the skill required to change, to know that part was the bad part and to change it, required like months, weeks, years perhaps worth of like reading, understanding about amplifiers, electronics, you're getting your soldering skills to a specific point, etc. So I was able to change that part because I'm skilled at soldering with the hot air station, and I knew exactly what part to change from probing the amplifier for 10 minutes and from past experience. So, you know, it doesn't always just go based on parts and time. It's also a little bit about what was the fault? How complex was it? You know, how much training would someone need to be able to figure that out from scratch? Man, there's so many dead op amps, like op amp graveyard. What we got? We got 1, 2, 3, 4. What the fuck? That one's like actually got a broken case there. That might have just been because it was on the floor or something. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a couple of 072Cs here, but I think that they were fine. I don't think that they were actually dead, so they could put those back in there. What's this? 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's it. I don't think there's any more. Wow. 10 dead, 0. Not all of these are dead, because sometimes it only killed one of them, but I don't trust these. I'm just going to put these to one side, just as a little kind of like souvenir, I guess. I don't know. Okay, cool. Right, so let's crack on then. New amplifier time, gentlemen. Ah, sweet like Danish. I do have a sweet spot for the B2 amps, and I love what Jay's doing with the brand. He has all the right things in mind for the brand. You know, it's not one of these brands that is, you know, banging out products just to make a quick buck. Jay is having equipment produced that he wholeheartedly believes is, you know, done right for the customer and for us fellow bassheads. So I've got lots of respect for B2 stuff. Even if the circuits themselves aren't bespoke, aren't, you know, unique to B2, even if they are kind of, you know, if they are designs that are factory kind of basic designs, they're actually built and tweaked to a much higher level to most other brands. So yeah, pretty awesome stuff. Okay, B2 Rage 2500.1. Let's see what this is all about then, and why it is in my workshop. Let's flip her over. Undo some screw rubies. Hey Bevis, did you get your tip for the soldering iron? Yes, I did. Thank you very much. I got my... here we go. There's two updates for you on that regard. I did get the tip for my soldering iron, which is awesome. It finally came through. Oh shit, my soldering iron's been on for ages. I hate doing that. I hate leaving the soldering iron on. I'm so pissed off about that. That's what fucking kills the tips. Ah, many frustrate. Many frustrate. I'm sure that you've done that before. It happens to me a lot when I'm live streaming, because, you know, I'll put the iron down, and I'll sort of talk a bit and do some stuff, and I'll forget it's on. But I'm sure a lot of you have done that. Left it on overnight, even perhaps for like, you know, 8 hours. Ah, my new tip. Anyway, yes, new tip came in, and also we also got this bad boy. Check this out. This is isopropyl alcohol, 99% pure, apparently. Now, actually, this is something that I wanted to do with you guys. Let's check. This was very cheap off Amazon. I was able to get 5 litres. Thank you very much to Elliot Vieras for pointing me in the direction of this, sending me the Amazon link. We have 5 litres of 99% pure, apparently, isopropyl alcohol. So we're going to just do a test now and see if it is actually the right stuff for what we need here. We need it to be completely non-conductive, which my old 99% was. But this was so cheap, so I'm just, you know, just thinking slightly, you know, is this legit? Just want to make sure it's legit, because it was very cheap for how much is in here. And we are, you know, we're in the pandemic where stuff like isopropyl alcohol is in quite high demand. I need a funnel or something. I need the funnel. Yeah, isopropyl was in quite high demand, so I just want to make sure that it is actually legit. How the hell am I going to do this? I need I could siphon it. I could spray it in. I could spray it in like this. That's going to take forever. Yeah, that's going to take forever. Let's not do that. Piece of paper? How much for 5 litres? It was £20, which is about 26 bucks maybe? Just fucking spills down the side, doesn't it? Urgh. There we go. A bit of it spilled down the side, but it's fine. There's so much in here, I don't really care. Right, I want to just make sure that this is definitely 99%. It evaporates quickly, like 99% does. That's one telltale sign, is how quickly it evaporates. The 70% stuff that I've got takes way longer to evaporate because of the impurities. So what we want to do is want to just go ahead and spray a little bit into. Want to get a puddle. Let's get a puddle on. Let's see. Let's get a puddle on something that's not conductive. Here we go. This bit of paper right here. There we go. This bit of paper. So let's get a puddle on this bit of paper. Take our multimeter, put it onto 2 mega ohms, and we want to make sure that there is no continuity in the puddle. So first of all, just check that there's no continuity on the paper. Make sure the paper is not conductive. Spray the puddle. Check for continuity. Awesome. Yeah, this shit's legit. I've got my probes right next to each other, literally less than a millimeter away, and we have greater than 2 mega ohms there. So yeah, this stuff is the real deal. Awesome. Thank you very much, Elliot. That is awesome. £20 for 5 litres of 99. That'll do me. Okay, one last screw. So this is B2 Rage Series 2500. So this is a 2.5K amplifier. Oh dear, this is a very stanky 2.5K amplifier now, by the looks of things. And yeah, this is a half bridge amplifier, but it is using the modern parts that you will find in some of the full bridge stuff. It's actually using pretty crazy output transistors for its size. Now let's take a look over this board. Let's take a look over the PCB. Let's see what we have here. Let's zoom in a little bit on here. I'll give you the zoom in cam. So power supply section then. The power supply section may look a bit different to what you're used to seeing in such a small amplifier. What we have here is we actually have, instead of having 1 or 2 large transformers, we have 1, 2, 3, 4, 5 small transformers which all parallel together to create the rail voltage and to provide power to the output section. So why do this? What's the difference between this and just having one large transformer? Well, from the research that I've been doing on transformers, and from people that I've been speaking to that do amplifier design, having multiple transformers in parallel like this is actually more reliable, stable and beneficial than having one single large transformer. The issues that come with having big transformers are negated by having multiple smaller ones in parallel like this. There are obviously some drawbacks to having multiple smaller parallel transformers, because obviously transformers themselves, they are susceptible to vibration damage, especially ones that are not that well seated down. Jay, look into this. This one especially, this one you can properly move that, and that is rubbing on these leads here. If you mount this to a box or anything that's slightly vibrating, that over time that transformer is going to short out, no doubt about it. That is moving way too much. There's no silicone or anything holding these transformers down. They are just in there from their leads. So yeah, that's one negative thing about having multiple transformers like this, is that there are more chances for vibration damage to occur on them. It only takes one lead to rub, and then you kill your power supply section. The output inductors, weirdly, are better seated down. We've got some kind of CA glue on here seating these down. You can see it has actually cracked there though. If you can see that there, it has actually cracked. So this amp definitely, I think, has been vibrated a bit by the looks of it. That CA glue is cracked. This one here moves. That's going to rub against the leads on the other side. Now, obviously, by having so many power supply transistors, also translates into the MOSFETs. So the MOSFETs here, we aren't running MOSFETs in parallel anymore. So these two MOSFETs, these first two, one will be for push and one will be for pull. So the MOSFETs aren't parallel. You're not running sort of like 4 or 5 MOSFETs in parallel with each other. You've just got one push, one pull per transformer, which is pretty cool. Now the output MOSFETs in these, they're using pretty goddamn crazy output MOSFETs. These are the IRFP 4868 MOSFETs. These are some of the biggest, most powerful, I think they're 300 volt? I can't remember actually, crap. They're either 300 or 250. IRFP 4868. They're either 250 or 300. I think they might be 300. Yep, I've got a feeling they're 300. What does it say here? 300, 300. Yep, 300 volt. So these are some of the craziest, beefiest 300 volt MOSFETs you can get on the market. In other amplifier designs that use these, like the Vibe, Black Death, Full Bridge series, Edge, Full Bridge amplifiers, and DS18, I think Wolfram do one as well, these output MOSFETs, there's something slightly poorly designed with the drive circuit or the filtration circuit. They run hot on idle, but they run unevenly hot. So like, you know, if the MOSFETs just did run hot because that's how they were in this circuit, like on high frequency class D amplifiers, the outputs do run hot on idle. But these MOSFETs, you'll have a whole bank of, you'll have a few banks of like 6 or 8 of these FETs, and you'll have 1 or 2 that get really hot and the others stay really, really stone cold. And that is just a poor kind of designed drive circuit or filtration circuit. The MOSFETs aren't paralleling very well. They're not driving very well in parallel with each other, which is why you end up with 1 or 2 getting hot, because the slight tolerance differences between those FETs are causing the ones that either have like a lower VGS, a lower VT. If any of those MOSFETs have a lower turn on voltage, then they will turn on first before any of the others in the board, and that can cause them to heat up because then they're on for a fraction of a second by themselves. So just things like that. But with these Rage amplifiers, I believe, from what I remember from working on these before, I think that the drive circuit is designed a lot better. I don't think that we have this uneven heating with these MOSFETs, but we're going to find out because we're going to repair it. So let's take this fully out of the PCB, fully out of the case, and let's do a quick cheeky repair on this. Going to try and keep this repair nice and quick. I'm not going to answer too much live chat while I'm doing this. We're going to do some live chat after I have got this up and running, because I don't want this stream to go on all night, like it has done in the last few days. Take my Allen key. Reese Carney, yo, hello buddy. How's it going, my man? Thank you very much. Hey, Reese on the Reese here. He has another one of those Hertz amplifiers. He has a Hertz HP1D, and the screen doesn't work. It powers up and doesn't have any output. And that amplifier is going to be coming to me pretty soon. So guys, who would like to see another Hertz HP1D? See what the issue is with that one. It would be so interesting if it's the same problem. So interesting if it's the same problem. 13 BTRX3, that looks very similar to the guts of my Orion XTR 2500.1. It probably is the same circuit design. Like I said, B2 don't design any of their own circuits in-house. So this will be a board design that is available from a factory, and there will be a few brands that, you know, might take it up. I imagine this is the kind of circuit design that Orion would definitely pick, because this is a pretty beastie, very high level, high-end circuit here. So yeah, I imagine it probably is the same one as the Orion are using. Yes, the screw downs. I'm pretty sure that Jay did this for me. You know, when we were talking about, you know, amplifier design and stuff like that with Jay, he actually said to me that he specifically requested the screw down clamps as opposed to the hammer clips, because I think he's probably seen me, you know, repair some amplifiers and see how much of a nightmare they are to take on and off. So I think the reason that Jay incorporates these is because he's seen these be repaired before, and he's kind of like, yeah, you know what, the screw downs are the way to go. So that is the way to go. Screw downs for sure. Okay, let's take this out. See what damage we have. So we already know that we've got a dead power supply section because we can see the power supply FETs have all smoked their guts. Now, one thing that I'm interested in, because these amplifiers are slightly susceptible to vibration damage, which you wouldn't really think because they are quite well seated down, but I've seen a couple of these amplifiers before with snapped rectifier legs. So the first thing I want to check is there any signs of fatigue on these legs? No, there's not. Okay, that's good. That's one positive. Output MOSFETs, is there any fatigue or snapping on any of the output MOSFET legs? Nope, doesn't seem to be there. Power supply MOSFETs, they all look well soldered in as well. And finally, one interesting thing about these amplifiers that could maybe kill the amplifier, I saw one of these amps come in. Now you see how the output driver card here is in headers, right? It's got this little foam thing on top. This little foam thing will prevent the driver card from walking out of the headers and, you know, blowing the output section from bad drive. But this one, let's just see, has this one walked out at all? Okay, it has actually shifted. So I was able to push that down, and it did go back into the legs quite a bit, quite far. It was probably sitting up about, I'd say about there. So we went from like, I don't know if I can show you, it's on the bigger camera. So we went from like about here to there. So it had walked its way out a little bit, which could have killed a couple output FETs if the gate drive was missing from one bank because the leg that drives it was kind of out of the header for a split second. Could have killed one of these, but I don't think that's what happened. Like, if I take this driver card out fully, I can feel that the legs make a contact with the pins in there. The pins make contact with the contacts at about this point here. So I don't think that it walked out far enough. It didn't come out far enough to actually disconnect. So I don't think that's the case. Alright, let's see. Do we have any dead output FETs then? That's the first thing. Dead output FETs will cause the power supply to fail like this. Let's see. First bank, we have the correct values here on this one. Now, because we've got two inductors, we have what we'll have is we've got 1, 2, 3, 4, 5, 6. So we've got 1, 2, 3, 4. That's interesting. 2 outputs, but we've got an odd number of FETs. Gate is this one. $54 ohms. Oh, I see. No, these are just working together. Okay, yeah. So although we've got 2 output inductors, we just have 3 MOSFETs which are linked here. These will be probably, I don't know, these low side. Yeah, these are low side. And then these ones over here are going to be high side. So we've got 3 low side FETs, 3 high side FETs. So we just got very simple output section, just one amplifier. These 2 inductors will maybe either be in series or parallel. I could work that out. But let's see. I think the output FETs are okay. Alright, so the power supply section appears to have died by itself. But power supply sections don't just die by themselves, guys. Something happened here. Now, what was I saying earlier about the transformers not being seated down so well? And there's a high chance of vibration, you know, causing this kind of thing to happen. Now, this is where you need to take a visual inspection quite closely. Now, I want to turn our attention to this transformer here. I noticed something earlier that I didn't like the look of. So, I don't know how well the camera is going to make it out. I'm going to try and spin her around a little bit so we can see in there. Yeah, okay. I don't know how well the camera makes it out, but just on this leg here, there is a little white. There's like a little white spark kind of, it's a bit like a bit of dust, like a bit of residue there from either a big spark or from some rubbing. It's like some kind of, you know, like some dust from the enamel rubbing off. Just there. this bit here. Now, obviously, I can actually draw in it with my... Look, I can get it, make it go away. So that right there, and there's another bit right there. I wonder whether this transformer has rubbed and is shorting between wines, which will have caused the power supply FETs to blow. So I'm just going to see if I can move them away from each other ever so slightly, perhaps. These ones are pretty well seated, I have to say, though. So it's going to be quite hard to see. So the only way that we're going to know, if that is the case, is to repair the power supply section, replace the power supply FETs, repair the drive circuit if it needs repairing. The drivers are just over here on this board. I'll give you the nice zoom in cam. So here's the SG3525, which is just another option. You can use a TL494, which is the common chip we're using the power supply, or if you have a little, if you this is a better chip to use. There's more options for kind of protection and dead time control and stuff like that with the SG3525. Pretty awesome chip to work with. And these right here are the drive transistors. So these are the power supply drivers. Now the gate resistors that we've got. This is another interesting thing which is worth talking about. These gate resistors, for these MOSFETs are IRFP 1405. These are not easy to drive. These are powerful, low RDS MOSFETs. The gate resistors are 270 ohms. That's not 27, that's 270 ohm gate resistors on these MOSFETs. What? Everything that we've been taught about gate resistor values is that with a higher gate charge MOSFET, higher input capacitance and lower RDS, you need a low value gate resistor in order to turn the FET on and off quickly and sharply in order to not have them to come on at the same time. You need a low value gate resistor so that they work properly. But here we have 270 ohm gate resistors, which is much higher than anything that we usually see from any other build house or amplifier circuit design. Yet we have really powerful MOSFETs here that would usually ask for low value gate resistors. So why is that? Now, it has been confirmed the reason that this is being done, the reason that these amplifiers are using high value gate resistors in the power supply section, is in order to cause the MOSFETs to like soft switch, or to kind of switch softer and less harshly than they would with a lower value gate resistor. By doing that, it reduces the amount of electromagnetic interference or RF noise that is thrown out from the power supply section and the transformers here, because they're turning on and off slower, softer. When we probe the wave coming off the back of these FETs, it's a lot more curvy. It doesn't have those big sharp spikes and rings to it like it would do when it's switching harder. And as a result of that, the high value resistors are fitted so that this amplifier passes some inspection that it needs to pass, whether in Europe or in the build house or in the country of origin. That's why it's done. It's to reduce the amount of electromagnetic radio frequency radiation noise emitting from the amplifier in order for it to pass some kind of regulation, some kind of test that allows it to be imported or exported somewhere. That's why that's there. It's nothing to do with, I don't think it's anything to do with making the amplifier perform better, perform more reliably. I think that these amplifiers would work better with, you know, normal sensible value gate resistors in here. For IRFP 1405s, I would want to see like 10 ohms, 22 ohms at most. Maybe even some of these amps are using 4.7 ohm gate resistors. But for a 1405, I don't want to see anything more than about 22 ohms really. So yeah, interesting one. It could be that this amplifier has died because the power supply FETs were sort of working softly, therefore not able to produce, you know, not able to pass their full current. If we look at the graphs on this, let's take a look. This is interesting stuff, guys. I know it's not technically amplifier repair, but it's kind of background information about this. Let's have a look. IRFP 1405 PBF. Let's take a look at this. Yep, we're on the right screen. Now I want to take a look at the data sheet. Now with a lower value, with a higher value gate resistor, okay, with a high value gate resistor, what we're going to have is we are going to have the FET turn on much slower. Because it's not after the FET has turned on, after the FET has initially turned on and the gate starts drawing a little current from its drive path, right? The curve on the drive is going to be very rounded, which means that the voltage at the gate isn't going to reach its peak until later on in the cycle. So if we take a look at the graph, I think there should be a graph that shows us the output current versus the gate voltage reference to source. Let's have a look. So we want drain source voltage, drain source voltage. We want current handling against gate voltage. I think there is a graph for this. Drain source voltage, no, drain source voltage, gate to source voltage. Here we go. This is the graph that we're looking at. This is the graph that we're looking for. So this is our gate to source voltage, and as this increases, okay, so gate to source voltage, we've got 5 volts on the gate, 6 volts, 7 volts, 8 volts, 9 volts, 10 volts, right? As the gate to source voltage increases, so does the drain to source current. The more voltage we have on the gate reference to source, the more current that this MOSFET can handle. Now there will be a cutoff point because obviously the package is limited to a certain amount of current. If we go up here, we can look at the package limit or current for this. Continuous drain current, silicon limited. So the package limit is around about 95 amps. That's continuous, that's not pulsed. So it's somewhere between the package limit and the pulse drain current, which is 640 amps. Absolutely monstrous amount of pulse drain current there. If we go down, we are obviously pulsing this MOSFET. We're pulsing this MOSFET, but not a single pulse. We're pulsing it. Where's it gone? Where's the graph gone that I was looking at? Drain source voltage, capacitance. Here we go, drain source current. So our package limit is about 95 amps, somewhere down here. Because we're pulsing it, we will be able to pass quite considerably more than 95 amps because we're not continuously passing it, it's happening in pulses. So as the gate voltage rises from 5, 6, 7, 8 volts, you can see that there is quite a considerable increase, quite a steep increase in the amount of current that this MOSFET can handle. So if the MOSFET is being turned on slowly with a high value gate resistor, then there's less time available where the MOSFET is being driven by a high voltage gate drive. There's less time available before it turns off for the current to pass with a high gate voltage up high. So that means that yes, it's probably going to run a bit hotter. The RDS, actually, is there a graph that shows us drain source resistance versus gate voltage? Drain to source, gate to source. I don't think there is. That's pretty specific. Gate to source, source to drain. No, there's not. Case temperature, junction temperature. No. Starting temperature. No. Okay. I was hoping for a gate to source versus RDS, but there's not. But yes, as obviously, if we turn the FET on sharply with a good gate charge for the whole duration that it's turned on, we'll get more time that the FET is on with the ability to pass higher current. So yeah, okay, so let's get cracking with this amplifier. Too much theory, not enough amplifier repair. Let's actually just cut all these off, makes life a little easier. Cut all these bad boys off of here, and then we're going to desolder them from the board the other side. Now these boards are obviously quite pretty. They're white, okay. B2 audio. Thinking about the customer. The customer might be looking at the guts. Might get a new amplifier, might pull it apart, be like, yeah, check this bad boy out. B2 amplifiers always look beautiful on the outside and on the inside. I love the white theme. It definitely is awesome. The sad thing is that when you blow the power supply section of an amplifier that looks this pretty with a white PCB, sadly, you know, it gets burnt, it gets ruined. I don't think that we're going to be able to clean that off to make it, you know, nice and white again. Dev Null, did we figure the Hertz amp? Yes, we believe so. I tested the Hertz amp at the start of this live stream for over 40 minutes. It must have been running over 40 minutes, and it didn't. You know, the op amps didn't die. The only thing that I changed was I didn't run my signal generator on the workbench. I ran a floating battery-powered frequency generator that more resembles how a head unit would run on the amplifier with a floating output ground. So I think that the Hertz amplifiers just don't like having a common output and power supply ground. I think that's must be what it is. Okay, so we've snapped off all of our MOSFETs here. I want to check the drive circuit health. Okay, so what we're going to do first is we're going to take a bit of rag and see if we can clean off some of the dirt on here, some of the janky stuff from all the MOSFETs burning. We won't be able to clean it all away, sadly. So this white PCB is going to be a little bit kind of blackened, unfortunately. Well, we can try and get some of it away at least. Now I believe that the drive circuit is going to be absolutely a-okay here. The reason that I think the drive circuit is going to be absolutely fine is because we're using such high value gate resistors. So we've got 270 ohm gate resistors between the MOSFETs and the drivers. So when the MOSFETs die, the 270 ohm gate resistors are going to drop a lot of voltage across them, enough that's probably going to allow the drivers to survive in a MOSFET catastrophic failure scenario. So I think the drive circuit is probably going to be absolutely fine. None of the gate resistors look burned, which is also a good sign that the drive circuit's probably fine. See if we can get in there with our toothbrush, get in between these caps a little bit. I think that'll probably do for now. There we go. So let's check drive circuit then. Hook some power up into this board. That's the 16 ohms pull down. That's my power. Well, sometimes I go, why the fuck have I got that in my head? No, stop. Do not sing that song. It's terrible. Power, ground, and remote. Power, ground, and remote. Boom, boom, boom. Okay, drive circuit is probably gonna be a-okay. Let's have a look. Oscilloscope, please. Switch it up to 10 microseconds. Reject low frequency. Up to 5 volts divide. And let's turn back on our measurements here. Clear measurements. Source 1, we want volts RMS. And we also want frequency. Channel 2, we want volts RMS. There we go. And we're back in business. 12 volts, which is a good sign. Now let's have a look at the drive circuit. Ta-da! Looks good to me. That's bank number 1. Bank number 2. Does that look identical? Yep, it does. All of these looking beautiful. Drive circuit, absolutely fine. No problems there. Excellent stuff. So we can pretty much go ahead and just fit new MOSFETs right away. We don't need to repair the drive circuit because it seems absolutely fine. Let's preheat the board a little bit before we get our soldering iron turned on. And what's going to be interesting about this is I'm going to be able to show you what the drive wave looks like when it has the 270 ohm resistors in it. And then we can have a look at what it looks like with a lower value gate resistor in it when I change them. And you can see why it's quite important to have the MOSFETs turn on and off quite quickly. Bro, remember DJ Monster, Sick Drop? Yeah, actually somebody reminded me about that song earlier. I got that sick drop. Sick drop. I mean, to be honest, let's be honest, guys. That was a freaking terrible song. Yes, the bass line dropped balls, but I mean that's a terrible song. His voice is jarring. I got that sick drop. Rolling on, I don't even know what he says. It's freaking. It is a very annoying voice. Most of the time, I couldn't actually hear what he was saying because the time period when I used to bump that track was when I had like Pioneers in the Proton, and I didn't really have any upgrades to the door speakers from what I remember. So it was kind of like factory door speakers, factory head unit kind of thing. Oh no, I did have the Hertz. I had the orange Hertz speakers in there for a while, didn't I? I can't remember if I used to still bump that track when I had those in. Yeah, Let My Beat Pound was actually a good track. If you listen to the lyrics of Let My Beat Pound, it's actually pretty good. Not a bad track. What was some of my other favourites I used to bump? Obviously, like, Late Night Tip was a good one, but it did drop a bit low. Like, the low note in Late Night Tip is pretty low. My van absolutely murders it now, but at the time it was quite low. Trying to think of what else I used to listen to. There was a track by Dr. P. What was it called? There was a track by Dr. P that was really good for bass. Taking chances. Taking chances. That is a good one. Also delusional. Delusional. I'm on my runs. Delusional. E40, yeah, there's a few E40 tracks that go low as well. My dog just growled at the screen. Oh, is that with my whistling about with Delusional? Oh yeah, Big Boss, yeah, Big Boss. Did anybody here actually like Bass I Love You? Did anybody actually like that track, or was it just like one that you played to see your woofers move? should we do actually? Hey guys, would you guys like that? What we could do one evening actually is I could go for a drive in the van. We could go and park up somewhere in the van with the DDZs. And I could whack all of my old school bass testers onto a USB. And we could kind of roll through them, kind of play some of the old stuff that I used to play when I had the 8s in my room or the JVC. Play some of those old bass testers, because the good thing about the Zs, now obviously, those bass testers from that time generally had quite high frequency bass lines in them. You know, they weren't super low frequency bass lines. They were quite punchy high bass lines. Now, fortunately, obviously the DDZs in a 6th order, they do play the higher stuff really well. So we could go for a little bump and we could do a live stream and we sort of bump out all of those old bass testers and bass tracks from back in the day. I can take requests from you guys live on the stream. I'd obviously have to set it up in a way so naturally it's going to be loud as frick. So the microphone's going to distort, but it depends what mic I use. It depends on how it distorts. I don't think I'm going to be able to do it so that it's clean, you know. Yeah, I think people are up for that. Bass I Love You is actually very relaxing at lower volumes. Kind of, but the problem is when you listen to Bass I Love You at low volumes, you just kind of realise how poorly produced it was. Actually, guys, you know what? You know what's my favourite bass tester of all time? And I don't say this like trying to blow my own trumpet or anything like that. But the Naruto rebass that I did, I specifically made that so that it played a really wide range of frequencies. I specifically made it so that the bass lines came in softly and smoothly, and they were round kind of bass kind of tones, so that it didn't kind of, you know, didn't impact or didn't like didn't come in too sharp, so that it was nice and round and smooth and predictable. So I really like, I mean, I'm sick of that track now. I've heard it so many times. Obviously, I'm making it, you hear it a lot of times, and then obviously I've used it a lot in my videos. So I'm quite sick of it now, but it's a very relaxing piece of music anyway, without the bass line. And the bass line, because it follows it musically, I did all my rebasses. I didn't do it in Audacity with like frequencies, like specific tones. I did it based on musical notes. So I would import the track that I wanted to rebass into Cubase. I would then tune a sine wave oscillator to the exact tuning of the track, because they're not all tuned perfectly to, like, you know, exact tuning. Like sometimes the file will be modified, or sometimes, you know, it'll be slightly out of tune with my Cubase whatever. So I then tune it exactly to the file, and then I would create a bass line that I felt would accompany the track well, while being a good range for testing subs out. And yeah, the Naruto, obviously, because it's a very evolving piece of music. It's not super repetitive. It tells a story. That track tells a story. So what that allowed me to do was create a bass line that rolled through all kinds of different frequencies and different sections and stuff like that, rather than just creating a kind of repeating bass line on a kind of repetitive rap track or dance track or something. I could you know, create a story. I could complement the story with its own deep bass track. Beverage, would you ever put line arrays in your room? No, I would never do that. A mic that records heavy bass without clip. Yes, I tell you what microphone would do that. A microphone like the pressure sensor in the Termlabs, or the SPL labs, if you hooked up the output of, because obviously the term lab, it actually gives you a kind of sine wave. It shows you that on the term lab screen. So it's obviously reading the sine waves. Now, if you were to then send that, connect that to a microphone input or a line level input, you could then actually listen to the tones and the sounds that it's picking up. Who would like to do that? Who would like to see me modify a term lab style or SPL lab style pressure sensor and turn it into a usable microphone that doesn't clip at up to, you know, pressures of 160, 170 dBs? That would be pretty cool, hey? The thing is, though, is it wouldn't sound that impressive. Like, the thing that sounds impressive, the thing that makes bass and subwoofer videos sound impressive is the microphone clip. The microphone clipping is what makes it sound loud. I don't use TikTok, but from the unfortunate few TikToks that I have seen, I've noticed that a lot of the music tracks that you can select in TikTok actually have the audio clipping already, or that the bass is already distorted, because it adds a kind of sense of like distortion and loudness. You know, it makes it seem loud by having that kind of distortion there. Adam says, Sam, my Audi is getting rehomed soon. I've got a Mark II Caddy van coming in, and all 815s are going in the 6th. 80 cubic foot. Wow, that's going to be something special. Fucking hell, that's going to be awesome. I can't wait to hear that, Adam. That's going to be sick. I think I saw the video where you showed us how to rebase. Yeah, that is an old video that I did a video on that. I hate music that has a ton of harmonics at low frequencies and all you hear is the harmonics, no bass at all. Yes, that is a problem with modern music. So much modern music that you listen to, especially like the kind of Drake type of stuff and the you know, Travis Scott and all that type of music, right? They'll have a bass line that sounds like it's going to drop absolute balls. Like it sounds like it's going to drop really awesome because there's like a low note in it. But what they do in production is the higher notes will actually contain the sine wave function in that note. Now when it drops super low on the lower note, they won't include much of the sine wave function at all, if anything, and it will just be a harmonic of that. And the reason that they do that is because they know that 95.9 whatever, like 98, 99% of people listening to that song are going to be listening to it on their phone speaker, on their cheap ass Bluetooth speaker, on their cheap ass home radio, like docking station or something, in their car, or their track is going to be played in nightclubs, okay? And out of all of those things, all of those systems don't produce the low frequencies particularly well. Some nightclubs, very few nightclubs can do it, but the PA stuff is generally like 38, 40 hertz and then it starts to roll off. So if you've got a note, if you want to include a note that would normally drop to say 28 in your song, from a producer's perspective, in terms of actually getting 98.8% of people to actually hear that low note, then they create a harmonic instead of actually the sine wave, so that you can still hear the bass line if your system's whack. So that's why they do it. And yeah, it's fucking frustrating because then you think, yeah, this track's going to be sick. You got big subs in your car. You go to listen to it and it plays the high notes great, and then the low note, there's like nothing. It's like, and you're like, eh? Here's a track that does it. Here's a track that does it, okay? Check out this track here. Here we go. I'm going to try not to get copyright striked here. Okay, this track. Let me turn my sound on so I can actually hear what we're doing here. This track has a potential for a sweet low bass line, but it doesn't. It doesn't have it. It doesn't actually have the sine wave in it. There's an advert. There's an advert first. 1 sec. Come on, skip ads. There we go. I do have ad blocker, but I'm not using Chrome just now. Here we go. This one.
Different with me. I see the things that they will for me.
Like that track, if you actually listen to the bass line of that track on the sub, it sounds whack. It's not there, but the notes, like you can imagine that the notes would be there and it would absolutely slam, but it just doesn't, because they're not there. It's just a harmonic. Right, so the output FETs that we are using here, the original ones are IRFP 1405s. We are dropping in some IRFP 7537s, which are actually a lot stronger. These are upgrades over the original ones. And the only reason that we're putting these in is because I got a sweet deal on these. There was actually a pricing error at RS Components, where I buy some of my parts from, and they actually listed these up, and I was able to get these parts for less than £1 each. I think they were like 91 pence each or something, and these parts should be like more nearer to £2.50 each. These are beast MOSFETs. So I took full advantage of the pricing error, and I ordered about 500 of them or something. Might even have been 1,000. I ordered absolutely hundreds of these because they were so cheap. So I've got so many of these, and obviously because they're beefy, I can use these in place of the classic 064Ns. I can use these in place of 1405. I can use these in place of 7530s, the really big ones that cost like loads of money. So yeah, it's happy days for me, because I got some cheap FETs that I can drop into pretty much anything. I wonder if the audio control epicenter would bring that down an octave or two. Yes, Weber, it would. That is exactly what the epicenter was originally designed for. I think back when, when everyone was listening to kind of bass on the radio, or when they were getting, when you were listening to the radio or stuff like that, I think there's a high pass filter applied to broadcast stuff that's broadcast over the airwaves. And so what the epicenter was designed to do was to listen to upper harmonics of that, and to then recreate it an octave or a couple of octaves down. It's also cool because some music just doesn't have a low bass line in it, so the epicenter is good at adding a bass line in real time that does follow the original music. So the epicenter is a cool piece of kit, but with modern music, with modern music that actually has a bass line present, the epicenter can actually sound really, really terrible, because it tries to, it gets a bit mixed up because there's already a bass line there. Now, just pushing these down to their correct height. Then we're going to solder them in. And I imagine that this is not the end of this repair. So I think that we're going to be seeing a transformer short somewhere. But in terms of like digital audio formats, MP3s and streaming, it won't. It doesn't kill the lower frequencies. The way that the compression works is it takes away some of the higher stuff and the details in the high end, and it takes away some of the kind of surroundy kind of stuff. Hard to explain, but if maybe I'll do a separate video on this because it's very interesting once you hear it. Have you ever done that thing where you got your iPod or your phone, and if you only plug your headphones in like slightly halfway, or you just back out your headphones a little bit, then the music sounds weird. It sounds like it's underwater. It sounds terrible. And what you're actually hearing is you're listening to only the sounds that are panned left, right. And some sounds are panned left, right, but like a nanosecond away from each other, which gives you a kind of surroundy kind of sound feel. So all the sounds that are centered, that are panned center, like the main vocals or like some drums, like the snares or the kicks, and all bass is centered. And when you back out your headphones a little bit, the way that it kind of, the signal gets grounded and stuff, you lose all of the centered stuff and you just hear the stuff that is panned mostly left, right. And when you do that, if you're listening to a 128 kilobytes per second MP3 track, it sounds terrible. It sounds all underwater. It's like that. And that stuff is actually in the track that you're listening to, but you don't notice it when there's everything else there. But if you then listen to a WAV format track or a FLAC or in a completely uncompressed and you back your headphones out, all of those sounds that you hear are clean. They don't sound at all. It's very interesting to hear the different levels of compression with MP3 like that. But MP3s and streaming, you don't lose any bass stuff. You just lose a lot higher details. Sam, no idea what you're talking about. I just turned 50 yesterday and I don't hear music anymore. I have to feel it these days, like the pressure from big bass. Oh man, that sucks. You know what? That is something that I'm quite scared about. Music and audio and sound is such a huge part of my life. One of the reasons why I've stopped listening to such loud music and why I don't drive my system at full tilt all the time now. I really don't want to fuck my ears, man. Like, when you kind of get when you start turning 30, when you get towards your 30s, and when you get to 30 and you start getting in your 30s, you're not old yet. You're still relatively fresh, but you are fully aware that you are not indestructible as you felt like you were when you were in your teens and when you were in your early 20s. So that you start being like, shit, my body is not indestructible, and it does get affected by stuff. So I'm kind of starting to back off with such crazy, because I want to get to the point, like by the point in your life where you can afford these ridiculously expensive speakers. Like, I want to have awesome, like hi-fi listening room. I want to have some of the sickest speakers. But by the time that I have the room for that and can afford that, I'm going to be quite a bit older, and I don't want by that time to have lost all my freaking hearing. So now there's no point, you know. Now I can't really appreciate that equipment as well as I could have done when I had better hearing. So, you know, I want to kind of try and look after it a bit so that I still have decent hearing by the time I can afford all the expensive speakers, you know. I think my hearing, because obviously as you get older, you lose the high frequency, you lose the higher stuff. So I can, at the moment, still hear up to about 16 kilohertz, right? Now, obviously, the way that YouTube works, it's probably going to filter this out. So I don't know if this is going to work. But if I just turn battery saver off for a minute. Have I got a charger down here? Let me just plug my phone into charge real quick. What I'm going to do, I'm going to play some high frequency through the microphone right now. And I want you to tell me, where do you stop being able to hear it? Let's do a quick little cheeky YouTube hearing test. This is not the best way to do it, but I think YouTube does still pass frequencies up to 20 kilohertz, even though the sound is compressed, because it's a pure sine wave. It should still pass it, and you should still be able to hear this. So if we go to our function generator right here, and we are going to let's have a look. Let's turn the volume right up. Gonna max out the volume. Yeah, that sounds pretty bad. Okay, so I'm going to start. I'm going to go here. Okay, so that's 10 kilohertz. Okay, so you should be able to hear that. This is 12 kilohertz. Okay, so you should be able to hear that. This is 14 kilohertz. So can anybody not hear this? Okay, I can still hear that. Let's go up a bit further. Okay, 15 kilohertz. This is 15 kilohertz. I am starting to not be able to hear that as much. I can still hear it. I can still tell it's there, but it's not quite as strong as the 14. Like I can tell that it's starting to roll off. So that's 15. Let's keep going. So a bunch of you guys can't hear that, can you? I can't hear it, yes. So who can hear it and who can't? Can everybody hear the 15 here? And it does depend on what you're listening with. If you're listening through your phone or whatever, your TV speakers might not be able to produce it. But that's 15. Now let's go up to 16. Let's see if you can hear 16. Okay, that's gone. I can't hear that now at all. So who can hear that? If you can hear that, I'm jealous, because I can't hear that. That's dead silent. Like I'm tapping on my phone right here, like this. Look, if I give you this frequency generator up to the microphone. So let's go. There you go. I cannot hear that at all. That is completely silent. Let's go up to 17. Who can hear 17? Who can hear 18? This is 18. 19. I doubt any of you can hear any higher than that. But mine rolls off about 15 and a half. I can't really hear the 16 anymore too greatly, which is sad. You know, it's kind of sad. I can't hear above the 15 anymore, really. You can hear the tapping. Yeah, that's obviously just the signal starting. But who can hear up to like 18, 19? Bass Starlet, yeah, it's annoying. How old are you? How old are you, Bass Starlet? So guys, give me your age and how high you could hear. Give me your age and how high you could hear. I bet that the older you are, the lower you could end up hearing. The phone can produce past 15k, and I'll tell you why the phone can produce past 15k. Because my RTA microphone level on my screen. So you see here, you see the RTA mic level. This was still going up when I moved my phone closer to the microphone with like 20 kilohertz playing. It does pick it up, and I have scoped it. It does pick it up on the screen and on Audacity and on the scope. So the phone does definitely play up that high. Let's see, what do we got? What do we got? 27, and you could hear up to 17. That's impressive. I am 29, and I am about 15 and a half. That's pretty impressive. Age 50 couldn't hear 14. Ah, man, that sucks. 39 could hear up to 18. Jason, damn, that's sick. That's awesome. Great hearing. 43, 14 kilohertz. Yeah, that probably sounds about right. I'm not far off that in terms of kilohertz. What else we got? Bass Starlet, 50. 27, I heard up to 16. It's similar to me, pretty much. 40 up to 15, 25, and I can hear up to about 16 and a half, 17. So most people, I think, are sort of between 14 and 17, I think. 43, deaf in one ear, I could hear 16. Oh, okay. So you can still hear up nice and high. 19, and I can hear up to 16. Oh, that's not so great. But it does depend on what you're listening to it through, obviously. Sorry, Adam. If anyone's got tinnitus, yeah, it's kind of annoying. Snipe X, are you only 16? Holy shit, dude. You know your shit. Snipe X has been giving me some tips and pieces and stuff on the old on some of the issues we were having with the hertz and other bits and pieces like that. I do not get the impression that Snipe, if you're really 16 years old, that's insane. You are hella mature and very knowledgeable for your age. Good on you. I'm 20 and I can hear 18.5. Awesome stuff. Do you have any videos on how to use an O-scope and prepare? I recently got a Tektronix scope and trying to find some vids. I have the plan. I have a plan to make a video where I show you what settings to use on your scope to repair amplifiers. So it's in the pipeline. It's probably be next year now though, because I'm doing STREAMMAS. Jack the Ripper couldn't hear past 14.2. Yeah, it sounds about normal. That's about normal. 29 can't hear above 50 hertz. Not sure how much into audio quality you are, but you notice how most remasters of old music sound worse and have way worse dynamic range. Yes, absolutely. I'm very much into high quality audio. I want to get myself some electrostatic speakers when I have the room for them. And yes, it freaking sucks. You like modern remasters, it's just an absolute compression war. It's a loudness war. Everything is compressed. Like, you know, everything is as loud as it can physically be within the limits. It sucks. Anyway, let's cut the legs off these FETs. Let's get this amp sorted. So with the drive circuit's fine. So the thing that we're looking for now is we're going to find out whether this amplifier has a shorted transformer or not. I believe it probably will do, because amplifiers don't generally kill their power supplies for no reason. And we did see some possible visual signs on the transformer that it had rubbed a lead. Okay, gentlemen, let's power her up and see what we got then. Turn the voltage down. I'm going to turn the voltage down to a nice safe level, about 10.5, 10.6 volts there. And we're going to probe the output. I'm going to probe the output of this MOSFET here. This MOSFET is on one of the on the transformer that looked like it had the issue. This is the push and this is the pull. So I'm going to probe between these two and see what kind of shaped drive wave we have on here. Oh, wow. Okay, so yeah, there's a short somewhere. The amplifier was drawing a lot of current. I actually had it I had 12 amps allowed. So look, if I go here, I'm going to allow 6.1 amps to pass. Now, if we take a look at the wave on the back of the FET here, yeah, it's drawing all of those 6, and the rail voltages aren't building at all. Actually, we have, well, no, sorry, I lie. We have negative rail voltage building. Yep, it gets to about 7 volts and stops. But the positive rail, we have absolutely nothing. So we either have maybe a shorted rectifier. These MOSFET parts, U30, D40C, are not the most reliable. So it's either shorted a rectifier randomly, or we do have a short in the transformer, preventing positive rail from building. Wow, yeah, let's have a look at the inputs of these rectifiers. So we're not actually getting an input. Oh, we are getting a tiny spike. Look at that. That's what we're getting to the input of one of these rectifiers. The rectifier itself is not getting hot. So I think that we do have a shorted transformer somewhere along here. Let's take a look at the other one. So the other rectifier, we do have, again, that same kind of dodgy shaped wave going down to the negative rail. So let's take a look at our MOSFETs again. Let's check one of the MOSFET banks that doesn't, that didn't have what looked like a bad transformer. And let's take a look at this one, for example. What does the wave on this one look like? About the same, I would say. What about the gate drive? Gate drive looks the same on all of these. So yeah, I think that we have a shorted transformer. Now, oh, that looks bigger. Yeah, you see now this one looks bigger. So the MOSFET all the way over this side, one of them over this side, that actually has quite a big wave on it. But the one over here that had maybe a dodgy looking transformer has a much smaller wave on it. So I think the one that we need to pay most attention to then is this one over here, the transformer that I originally picked this one out as being one that could be bad. Another way to have a look and see, to kind of, if you can't see anything on the transformers in terms of like visible damage, but you think you might have a shorted transformer, take out your thermal imager, see which MOSFETs are getting hot first, because the ones that are driving the shorted transformer will probably get hot first, right? So let's take our thermal imaging camera right here, have a quick look across the selection of all power supply MOSFETs, and let's see if any of them get hot first. No, I think they're actually all kind of heating up evenly. We've got like a couple over here maybe look like they're getting hotter first, but I still don't trust this one over here. So now what I'm going to do is I'm going to fire it up again. This time I'm going to like twist and turn some of these transformers here to see if the current draw or the rail voltage changes at all. So let's take my oscilloscope probe and we're going to probe the rectifiers because the shape of the wave on the rectifiers will change if the short on the transformers disappears. We're also just going to check the rectifiers for shorts very quickly because we can do that now. Let's have a look. What do we have? Oh, okay, you know what? This MOSFET, this rectifier actually appears to be shorted. Interesting. I wonder if the rectifier might have got shorted by a a transformer short. If it might have like spiked a bunch of voltage this way, might have even acted a bit like a flyback. Or whether it just died on its own, because these MOSFET parts are kind of janky. They're not that great. So let's remove that rectifier then, and let's see whether replacing that fixes it. So let's get this cooked up. Got some pretty high thermal mass on these pads. Good old B2. Producing an amplifier with nice thick PCB, as always. So that should just come right out now. Fucking thing, come on. It's actually loose in the holes now. It's not even soldered in anymore. Come on, it's just like a little bit of solder or something. There we go. Excellent. Okay, so now that's removed, let's see if the short has disappeared from the board here. Yeah, so the short has now disappeared. We now have charging capacitor type of thing on the multimeter. So yeah, this part then, this MOSFET rectifier appears, yeah, it is. It's shorted between legs 2 and 3. Look at that. Now this is very rare for a rectifier to be shorted. That rarely ever happens. So this is a pretty rare fault. And I've only ever really seen the MOSFET rectifiers go bad, like on a more regular basis. These are not particularly great quality parts. So this is a MOSFET U30D40C. And the type of rectifier that this is, does it show us on the bottom there? Yeah, we have the two diodes facing each other. So looking for something, and I think this is going to be, what's that, 30 amp 400 volt, is that? Or is that 30 volt for, it might be 300 volt 40 amp. Let's have a quick look on the online. U30D40C. See what we got. These are actually available to buy. I thought these were going to be difficult to buy. What's this? Here we go. We got 400 volt 30 amp. Okay, cool. Yeah, so it was the first way round that I said. 30 amps, 400 volts. So we can discard that, put that to one side. Let's see if I have any spares of those in my drawer down here. Why is B2 using inferior parts? B2 aren't using inferior parts, but it's just the factory that uses those. To be fair, like Jay, who owns B2, he might not be aware of the quality differences between the MOSFET parts and other brands. It's something that someone like me would have to tell him at the point of manufacture. So if Jay was looking at manufacturing an amplifier and he wanted to come to me and say, Sam, here's some prototypes of the amplifier, check them out, see what parts we're using, see if they're any good, etc, etc. At that point, I could then go through and say, yeah, this is fine, but I could say, you know, maybe swap out these rectifiers, if you can, for something a little bit better. Some of the Sundown amplifiers have used these MOSFET parts in the past. Look, here we go. There's another MOSFET. There's a MOSFET part in here. Look at this. This is a U20D40. So this is a 20 amp 400 volt part. And look at what happened to this one. That's pretty insane. It's still, all the legs are still just about connected there. Okay, in terms of replacement parts, I've got some U20 D40s, which are not as high current. They are 400 volt, 20 amp. They should work fine, but I'm not going to put, you know, lower current parts in than what B2 were using originally. I just found this FEP 30. Is that right? FEP 30JP. Let's remind myself what that is. FEP 30JP. That's a 600 volt 30 amp. Okay, that should work. Yep, that'll work just fine. Now with rectifiers, they're not like FETs. You don't have to match batches. You don't have to use the exact same. So it's provided the rectifier can pass the current and the voltage that you're giving it, and provided it's fast enough, then it'll work absolutely fine. So yeah, I think we're going to drop this one in, seeing as it's the one that I happen to have here. Actually, oh no, I've got a U30 D20A here, but this one isn't probably going to be any good because it's only 200 volts, and the original part in here was a 300 volt. No, it was a 400 volt. Do we really need a 400 volt rectifier in here? What's the I wonder what the voltages across that are. So for a 400 volt part, the voltages would have to be plus minus, you know, 150 volts. Which I don't know. Actually, they might be. This is a half bridge amplifier, so they might be. So let's stick our 600 volt part in. I found that Maxonics uses smoke signals for FETs. Yep. Do you see Nippon Chemicon caps much? Not really. No. So obviously most of the amplifiers that I'm repairing and stuff are mono subwoofer amplifiers, quite high power amplifiers. And the quality of rail capacitor is much less important in a Class D, especially with a subwoofer Class D amplifier. I think I talked through this a little bit on one of my other live streams this month. About how where Class AB is a linear amplifier, the rail voltages, the sine wave is being applied directly to whatever's on the rail voltage. So in a Class AB amplifier, if your rail voltage is kind of doing this, you know, at a very fast speed, but if your rail voltage has any noise on it or any fluctuation on it, then that fluctuation and noise will be also applied to the sine wave that is being applied to the rail voltage. But with a Class D amplifier, the rail voltages, the rail capacitors are just for kind of buffering and filtering of the rectified switching waves from the power supply. The audio wave is actually made up of pulses referenced to the two rails. So yeah, any small noise will kind of still be on this sine wave a little bit, but this is all high pass. This is low pass filtered with inductors and stuff like that after this is made. So I think you've got more noise created by the Class D environment itself, you know, by a Class D amplifier itself, than you're ever really going to have by different qualities of rail capacitor in a Class D amplifier. The only thing you benefit from having better quality of rail capacitors in a Class D bass amplifier is just reliability. You know, how long do they last? And stuff like that. But in terms of actual quality of sound, firstly, it's a sub amp. You don't care about quality of the sine wave coming out too much, not like you do with a Class AB or like you do with a full range amplifier, because subwoofers, low frequency, slow, can't produce high frequencies, so it doesn't really matter if the sine wave is a little bit more, you know, noisy than it would be with a Class AB or with better caps. It's not so important. Okay, let's cut those legs off of this one. power it up and see if that was the cause of failure. Was that the reason that this failed then? So we're going to probe the, what we're going to do, we're going to probe the, going to probe the input to these rectifiers here. See whether it comes on fully now. See whether we get a nice big square wave on there. Hey, there we go. That looked good, didn't it? That looks tasty. Now, we should have built a little bit of rail voltage. So we've got 19 volts of positive rail and we've got 19 volts of negative rail. Excellent stuff. Let's check the output section real quick. So we've got high side. No, that should be low side, isn't it? Yeah, low side, sorry. Low side, that looks good. High side, that looks good. So let's probe the low side FET drain and we should get the switching wave come up on the screen here when it activates. Okay, oh wait, there we go. There it is. Boom. There it is, gentlemen. Amplifier is fully repaired. We have a blue light on the side. We have output switching. Now, here we go. Yes, B2. Well, not B2. But this is great. This is freaking great. This is what I like to see. So, whoever designed this board actually took note of, they actually thought a little bit about this. Right. These MOSFETs here that are being used in the output section, these are IRFP 4868. IRFP 4868. These are very, very high current, low RDS MOSFETs. They're very hard to drive. They take ages to turn on and they take ages to turn off. Okay? Now these MOSFETs, they use these MOSFETs in the Korean Xenon factory full range Class D full bridge amplifiers like Vibe, Edge, DS18, I think Wolfram does one. And those MOSFETs, they all run hot at different levels. They don't run very well at all. The output MOSFETs run hot, run unevenly hot, and it's not a very well designed circuit. And the output switching frequency in those amplifiers is actually quite high. It's like at about 150 kilohertz or something like that. And I think that's too fast for these MOSFETs. I don't think these MOSFETs in that circuit need to be or want to be switching that fast. Now, they need to be switching quite fast because they're selling that as a full range amplifier. But to be honest, most people aren't going to be using that as a full range amplifier. It's 10,000 watts RMS for the bigger one. Who's going to, well, there are some people that might use that on mids, but not really, like not high frequencies, not like tweeters and stuff like that. They're predominantly going to be used as subwoofer amplifiers. So what we have here is we have an amplifier using the same output MOSFETs, but the switching frequency is sensible for a subwoofer amplifier, 70 kilohertz. So it's going to take the sampling frequency of the sine wave is 70 kilohertz, which is absolutely fine. It's fast enough for subwoofer amplifier application, more than fast enough. But what it means is that the output FETs are turning on and off slower, which means that they have more time. It's a much more relaxed environment for them to be in terms of switching. And because these are slow, sluggish, high gate capacitance, high gate charge MOSFETs, a slower switching environment will mean that they will run much cooler than they would if they were in a faster switching environment. So check this out. These MOSFETs always run hot in the Korean amplifier, in the Xenon one. So let's turn this amplifier back on. Let's get the scope on run. We've got 12 volts going in there. And let's just have a look and see whether these FETs, I imagine they'll, warm up a little bit. They might warm up a touch, but we're going to compare it to how hot they run in the Xenon full bridge amplifiers. In the Xenon full bridge amplifiers, after a few minutes of operation, these MOSFETs are sitting at like 60, 70 or 80 degrees Celsius when they're not attached to a heatsink. Let's have a look at what we have here. So there's a couple of hotspots on the board. Those hotspots are these blue capacitors. See that? These two blue capacitors, these do run a bit hot. They're doing some pretty intense filtering. So that's those. But the actual MOSFETs themselves, we have 26 degrees on that one. 28, that's not so bad. 28, 27, 28. So they're all heating up a little bit. But if we were doing this same test with the xenon one, right? Some of these MOSFETs right now would be at over 60 degrees Celsius. 29, 30. So yeah, they're very hard to drive MOSFETs. They will run a little warm, which is fine. And they're all even. That's the important thing as well. They're all heating evenly to the same temperature. The issue is with on these Xenon full bridge amplifiers that are using these FETs at higher frequency, the heating isn't even. There'll be one FET that gets to like 70 degrees and the other one's at 22. Shitty design. Sort it out. Thank you to whoever designed this circuit for selecting a lower switching frequency on the output section. Much better, much more reliable. Like it. Just use better quality rectifiers next time, and then this won't happen. My throat is killing me. I've been shouting and talking like live streams for hours the last like however many evenings. So gentlemen, on this live stream we have figured out probably what the issues were with the Hertz amplifiers. We've sorted that out. Actually, I just want to make sure, I'm just going to power it up one more time. I want to make sure that if I twiddle and twist these, it doesn't turn the amp off. You know, it doesn't like cause current draw or anything like that. I just want to make sure that there isn't... oh yes, there's actually one thing left that we need to do with this amplifier. Yeah, that's fine. There's no damage to that yet. But there is one thing left that I was going to talk about with this amplifier. Remember how earlier I said about the high value gate resistors being used in order to kind of soft switch the power supply FETs. Take a look at this. Now obviously these aren't the original FETs. These are the 7537s which I'm now using, which might be slightly easier to drive, I can't remember. But let's have a look at the shape of the wave on the power supply FET here. See, this is way more curvy and way more slanted than you're probably used to seeing. Now let's look at the gate drive shape. My dear Lord, look at that stanky wave. Let's AC couple that, get that on the screen a little bit better. Let's noise reject and what are we doing? Low frequency reject. There we go. Look at the shape of that wave. So let's pause that and let's explain what's going on here, all right? Let's fuck it, I don't know. Let's DC couple it. I want to read the voltage correctly. It's a shame. It's a shame that my scope goes all the way up. Fucking. I want to be somewhere in between these two. I want to be like. Okay, whatever. Let's just go on this one. Let's go on that one. That's fine. Okay, so if we take a look here, so the FET is turning on. Okay, the point where the FET turns on is here. That point right there. Here's where the FET turns on. There we go, that's fine. Leave it at that. That's where the FET turns on. Nope, one more time. I just realised I can increase the voltage and I can get that higher on the screen with the other view. 5 volts divide. Let's go up to 12, 13, 14. There we go. That's better. That's much better. Okay, that's much better. So this right here is the point where the FET turns on. Okay, so you can see that it's quite a steep slope on the drive before the FET turns on. Okay, that's because the FET isn't really drawing any current from the drive circuit yet. So it's quite sharp. It would go all the way up here. It would go right up here and turn on nice and quick. However, this little dip here, this is where the MOSFET turns on. This is the threshold. This is the gate threshold. So we know that this MOSFET has what looks like a 4.5 volt VT, which is actually confirmed by my transistor tester here when we test the transistors. So the turn-on voltage of these FETs is about 4.5-ish volts by the time that the FET comes on. Now, after the FET has turned on, you can see that the charging of the gate is very slow. It's properly like curvy. So the MOSFET here, it takes all this time to turn on. Now for this whole time, from this point right here, let me grab something pointy so I can point at the screen. From this point right here to this point right here, there we go. From this point right here to this point right here, the MOSFET is turned on. So in an ideal world, you want this part here where the MOSFET is turned on to be fully square. And that will mean that there is maximum gate charge available to the MOSFET while it is passing current. In this instance, I believe what we'll have such a slow turn on that while this MOSFET is able to pass current, especially for this first part of this wave here, the gate's voltage is that's like 5 volts, 6 volts, 7 volts, 8 volts, 9 volts. It's not that high for this whole time. And only by this point here, we have 5, 10, we have about 12 volts worth of maximum gate drive there. The maximum gate drive at 12 volts is only present for a very short period of time before the MOSFET turns off again, and it takes bloody ages to turn off. You can see that the wave starts here, stops there. It takes bloody ages to turn off because of that hugely high value gate resistor. So for this whole time that it's turning off, this downward slope, it's still able to pass current through the MOSFET during this downward slope because it's not turned off yet. The point where it turns off is here, at this little bump. This point right here is where the MOSFET turns off. So we have a big chunk here on the downward slope and a big chunk here on the upward slope where we are missing potential current passing ability by turning this MOSFET on so slowly. And the effects of that means that, you know, we don't have quite as much high frequency ringing through the board. If we turn this back on again, okay, and we have a look at the wave shape on the MOSFET output, let's probe the output of the MOSFET. Okay, so you can see it's quite curvy. Now, usually you would see some big spikes. You'd see some like big ringing here at the start of the wave. But because it's softly switching the MOSFET, we don't get that. So there's no noise generated there. If we probe the output wave of the transformers, it also looks great. We don't have any ringing here. It's very, very smooth. That's because it's switching very, very softly. Especially if we go down into the lower voltages. Look how curvy that goes. So we trade some ability to pass current for some cleaner kind of non-noisy electromagnetic or radio frequency noise operation. I think I generally prefer amplifiers to perform at their best. So, do I have any resistors here that are the right size that I can drop in that are like a lower resistance that we can show you how it probably should look? I've got some 47 ohms. They're a bit higher than what I would normally use. For these MOSFETs, I would probably like to put 22s, 10s, or even 4 points. Here we go. I've got some 3R3s. Oh, that might be a good example. 3.3 ohm gate resistance. That might be a great example because that's very, very low. What else have we got? I've got some 10s, but they're a bit small for these pads. Right then, guys, I'm going to give you the choice on this one. What do you think we should go for? So at the moment, we've got 270 ohm gate resistors. I can either put in some 47 ohm gate resistors, which I think will be a nice balance between allowing a lot more gate charge into the FET quicker and turn off quicker. Obviously, that 47 is a lot lower than 270, but still high enough that it's not switching super hard and there's not like super loads of ringing going on. Or I can put in the 3R3s, which will turn these FETs on and off in the blink of an eye, but I think that we'll get some ringing at the start of the wave on the transformers here. So what do you reckon? I don't have 22s. I don't have 22s that are the right size. I do have some 22s and I do have some 10s, but they're too small for these pads. Like, these pads are quite big, so I could do it, but it would just look a bit janky. You know, they wouldn't look like the right size. It would be fine. It would be okay because we don't need much current for. We all got some 34 ohms in a smaller size. Most people are going for 47. Okay. All right then. Let's drop in a 47. So you can see the difference here. I'm going to show you the difference between the very, very high value 270 ohms versus the 47 ohms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's 10 there. I want to show you this on the zoom in cam, but it's too close to the edge of my desk and it's all falling off. Oh, there you go, I can do that. There we go. I'll show you on the zoom in cam just for the first couple. Okay, now a little bit of flux to reuse that solder that was there. A little bit of flux will get that nicely in. These are pretty new amplifiers, so you know all the solder's pretty fresh anyway. Don't really need to use any fresh solder. And just use the original with a bit of flux. There we go, soldered on beautifully. You would never know that these were changed once I clean the board from the flux. I'm sure I counted out 10 of these. I'm missing 2. Can I not count to 10? It's like 1, 2, 4, 5, 6, 7, 8, 9, 10. What the hell? I'm sure you guys watched me count 10 of these. Okay, are you ready to see then what difference it makes having lower value gate resistors in the board? Okay, so now we have 47 ohms all in the board. Let's power her back up and let's see what the shape of the wave looks like. It probably won't look quite as good as I wanted. Like 22 would probably be the sweet spot for these, or maybe 10, but I don't have them in the right size. But I think 47 is a nice kind of bit, a nice middle point between the 270 that was there and something that's really hard switching. So yeah, let's put our oscilloscope probe on the back of the FETs here. Just double check, do a quick visual inspection, make sure these are all soldered correctly and I didn't put any wrong ones in. 470, 470, yep, all looks great to me. So power supply goes back on. Now let's have a look at the difference in the shape on the waveform here. Okay, so you see how much sharper that is. Now, what's funny is we do have a little dip on the sine wave there. And do you know why that is? That is because the power supply drive circuit here is not driving these to 50% duty cycle. That is very interesting. I wonder if that's to cater for the fact that it didn't have... Yeah, this isn't 50% duty cycle. Right, let's take a look at the drive wave to start with here. Let's go up to 14 volts. Now look at the drive wave. How much better does that look? All of a sudden, we now can no longer see a spike when the FET turns on. And we can barely just see a tiny little spike where the FET turns off. Now we have, for the whole duration that this FET is turned on, we have the gate charge pretty much maxed out, allowing for really, really good full current through these FETs for the duration that they're turned on. Now what I've noticed though, which is really, really interesting, is that the duty cycle is not 50%, which means that these power supply section is not running at its full potential. What is the duty cycle of these? Let's take a look. Now obviously 50% duty cycle will mean that the high side turns off as the low side turns on instantaneously. With the duty cycle being lower than 50%, what you have is you'll have the high side be like on, off, and then there'll be a bit of dead time before the low side one turns on. So it'll be more like rather than like that. And what that means is that actually there'll be slightly lower rail voltages present on the output section than if it was at 50% duty cycle. Now the SG3525 chip, sometimes these are designed and set up so that the duty cycle varies with either load on the speaker terminals or input signal from the RCAs. So if we put some input signal from the RCAs in now and we crank it up, we might find that the duty cycle does go to 50%. But just so you can see it on the scope screen here, let's turn it back on and let's show you what the duty cycle percentage is. And in order to do that, I need to go to my measurement screen here, clear all of these, go to probe 1, we want volts RMS, and then go to time and we want duty cycle. So if we press on duty cycle, that will tell us the percentage of time that this FET is turned on in the cycle. So on the output, it is 50% duty cycle because of the way that the MOSFETs work. Like this little dip here is a hint that it's not 50% duty cycle. But if we go to the gate, we can see here that the gate is showing a 36% duty cycle. So the MOSFETs are only being turned on for 36% of the time, and the remaining I suck at maths percent of time, it's not turning them on, which is really interesting. Even if we crank up the voltage and stuff, it doesn't change that. So usually in most amplifiers, that duty cycle is at 50%. So I wonder if we apply some RCA signal, does it bump that up to 50%, I wonder? So let's get my frequency generator here, and let's figure out which is the RCA inputs. It is the one furthest from the LEDs. Furthest from the LEDs is the RCA input. Okay, RCA is in. Let's go to our frequency generator mode on here. SPR Lab Next LCD. dB testing, sine wave, 50 Hertz, level 10%. Okay, let's make sure the gain's down low on here to start with. Actually, no, let's turn the gain up to about halfway. Let's turn the gain up to about just over halfway. Turn all the other knobs down to 0. There we go, and make sure I'm master. Okay, now let's turn the amplifier on and see whether the duty cycle changes as we increase the RCA signal level, as it does in some amplifiers based on the 3525. Okay, so amplifier coming on now. 36% duty cycle. Now I'm going to start the sine wave. And we're going to also start the sine wave. Okay, sine wave is playing. Let's increase the gain. No, I'm increasing the gain and the duty cycle is still 36%. What does the sine wave look like on the output? So I just want to I want to get to clipping point, because obviously at clipping point that would be when the amplifier is working its hardest. Okay, whoa, let's zoom out a bit on that. There we go. Get rid of that one. Source trigger 2. Reject high frequency. Come down a bit there. There we go. So how far are we from clipping then? Okay, there's our clipping point. Just about. Oh, it starts clipping the high rail before the low rail. See that? Slightly imbalanced rails there. So this is just below clipping point then. So that's just below clipping point. And what do we have? We have source 1. Still we have 36% duty cycle. So not only then, maybe that makes sense. What a stupid design. Why would they do that? They've deliberately bottlenecked. They've deliberately handicapped this power supply section just for the EM noise regulations. So not only have they fitted the 270 ohm gate resistors, which causes the FETs to switch slower, to prevent the FETs from overlapping each other during switching, the dead time has been massively reduced, so there's a big gap between the push and pull turning on, which will prevent the MOSFETs in the power supply section from overlapping because they're switching slower. Makes sense. So now that we've fitted lower value gate resistors, we could technically and essentially we could increase the duty cycle from the SG3525 to, you know, get more potential power into the output section. Let's have a look. But what we need to take care of as well is by increasing the duty cycle on the gates, we will increase the rail voltages slightly. So what I want to do first, before we actually do that, I want to see how far away from the rails are we from the MOSFETs limit. So these MOSFETs are 300 volt MOSFETs, okay? So what I want to do is go to my scope screen now. I want to go to here, clear messages again. I want to go to voltage RMS, and I also want to go voltage peak to peak. that's going to tell us our peak-to-peak switching voltage on the output FETs. I want to make sure that that is not anywhere near 300 volts. If it gets near 300 with the duty cycle still at 36%, then I shouldn't increase it because it will cause more rail voltage to be present. So now let's go and have a look. Let's turn this on to 50 volts divide, turn the amplifier back on, and we're going to crank up the voltage. We're going to crank up the voltage from 11 volts. Oh, let's stop the RCA. Don't need any signal going in just now. We're going to crank up the voltage. See, here we go. Got peak to peak of 164. That's with 11 volts worth of input. So if we go up, 14.8 volts, we have 225. 15.2, 15.6, 15 points. So we've got 16 volts, and we're at 239 volts worth of peak to peak. That is safe. If I increase the dead time to, I don't know, say 48%, giving a 2% dead time for the MOSFETs to switch over, we should get a bit more rail voltage, but it will still be under the 300 volt limit, which means that this amplifier will do more power. This is a little power increase mod. SnipeX, this modification can also decrease switching losses. Yes, I still can't believe that you're 16 years old. Right, guys, let's have a look at the chip then. SG3525. What is it? This one, AP. Doesn't really matter what the suffix is. So we just need to figure out which pins are responsible for setting dead time and duty cycle on this. Oh, clicked the wrong link. Go back. Datasheet. Okay. So what do we have here? We have inverted input 1 to sync oscillator output, CTRT. Here we go. These are the timing. This is the timing resistor and timing capacitor. So that's what's going to set the oscillation frequency. But we want the dead time to discharge, VREF, output 1, output jump down comp. Okay, I can't quite see which one it is from here. Let's go and have a look at the rest of the data sheet. And see discharge, which one is going to be setting the, here we go, duty cycle, maximum duty cycle. Okay, so the maximum duty cycle might actually be 45%. PWM comparator. Oh, that's a comparator. Output drivers, here we go, output drivers, high level standby current. I might have to do a cheeky Control F. Error amplifier oscillator section. PWM latch, soft start input, inverted input comp discharge. Maybe it's the sync. Maybe it's the sync one. Pin 3. It might be the sync, or it could be discharge. So on a TL494, the dead time is set by pin 4. Now what's the dead time on? I think that's just called... I think on the TL494, I think that's literally just called dead time. Here we go, scroll in a bit on this one. So pin 4 is called DTC, literally dead time control. But on the 3525, we have the timing resistor and capacitor, which is going to set the frequency, and then we don't have anything else that immediately suggests dead time control. Anybody in the live chat got any ideas? Let me just do a quick Google search. There we go. It says adjustable dead time control, but tell me how. Which pin is it? Using no. Maybe Google Images will help. I see. I see. Okay, this works slightly differently here. So with the SG3525, I think the timing resistor and the timing capacitor, one of these does the speed and one of these maybe does the dead time. Whereas on the TL494, we have the resistor and capacitor, they actually connect to each other, and it's the capacitance and resistance between them that sets the frequency. Snipex says pin 5 and 7 lower the resistor to lower the dead time. But pin 5, hang on a minute, pin 5 and 7 are 5 and 7. Oh, 5 and discharge. Okay. So between pin 5 and pin 7, we should have, you're saying, a resistor? Looks like from what I understand from the TL494 circuits, that would usually just be a capacitor. But let's have a look. Let's bring this over here into view. So let's turn this off, get the voltage sunk down to ground, and let's have a probe with our multimeter. This is exciting shit. I want to make this quick mod. This is going to be good if it works. So pin 5 and 7. 1, 2, 3, 4, 5. Here we go. C503. And pin 7, 5, 6, 7. I don't think there's anything connected to pin 7. Pin 7 doesn't have a trace coming off it, doesn't look like. Oh no, wait. Pin 7 is connected to R508 at a 561. So out of pin 5, 1, 2, 3, 4, 5, we have C503 directly. After C503, we have, I just want to make sure we don't have ground. Okay, no, we do have ground. So pin 5 is connected to a capacitor that goes directly to ground after it, I think. Yep. So pin 5 is grounded through a capacitor. Pin number 6 is grounded through a resistor. So pin 5 is grounded through a capacitor and pin 6 is grounded through a resistor. And that resistor is 10 kilo ohms, a 10k resistor, a 10-3. It's hilarious. Every time you say duty, my grandson can't stop laughing. Oh, so how would you say it? Would you say duty? Duty cycle? But I say duty with like a du, with like a, I spell it like this. I spell it like D-U-T with a Y, duty cycle. Whereas you probably say duty, like that, duty cycle. That's pretty funny. Be careful, you may need a bigger dead time to prevent the transformer building magnetic flux in a staircase fashion in case of uneven switching or loading pulse. So I was going to try, I was hoping that I could vary the dead time with a resistor, with a variable resistor, so I could slowly turn it up and I could watch for the current draw on the power supply. If it was starting to creep up, then I'd know that we were starting to get that happening. But I think 36% is just a bit low, like, don't you? What, like, at least 42, at least 45? So, okay, let's just very quickly, let's watch the YouTube video that came up on this one here, SG3525 dead time control. Let's watch this video and see if we can learn together exactly what we're doing here. Oh man, adverts, because I haven't got what's it called? I haven't got ad blocker on Firefox. Oh no, it's not in English, is it?
आईसी का डेट टाइम को कंट्रोल करने वाले हैं या कभी-कभी आप लोग डेट टाइम को कंट्रोल नहीं कर पाते हो, इसके ऊपर भी डिस्कस
It's not in English, but we may be able to still figure it out.
देखिए डेट टाइम होता क्या है वो समझ लेते हैं. यहाँ पे एक आरडी लगा हुआ होता है जिसको हम लोग
Here we go. So there should be a resistance, yes, between pin 5 and 7, as Snipex correctly said. Between 5 and ground and 7 and ground, capacitor resistor adjusts operating frequency. Right, okay, that might be what this is.
डिस्चार्ज कहते हैं और यही रिस्पॉन्सिबल होता है डेट टाइम को कंट्रोल करने के लिए. डेट टाइम का मतलब होता है कि दोनों ही पल्स जो सिग्नल 1 और सिग्नल 2 उस टाइम में ऑफ स्टेट में रहेगा. देखिए यहाँ पे दोनों ही सिग्नल ऑफ स्टेट में आपको
I have no idea what you're saying, bruv. What?
दिख रहा है। जैसे डिस्चार्ज रेजिस्टर का वैल्यू तो उसके पीछे काफी रेजिस्टर का वैल्यू 500 ओम से ज्यादा नहीं होना चाहिए, लेकिन अगर यहाँ पे रिक्वायरमेंट
Oh, that was interesting. Dead time resistor range. 500 ohms is the maximum here, hey? So, what do we have here? We're looking for potentially a low value resistor. Let's take a look back on our board real quick. So, over here, there was a resistor that was connected to pin 7, which is this one here, R508. And this is a 560 ohm resistor by the looks of it. So, perhaps this is dead time. Perhaps this is setting dead time. So wait, what was that on the data sheet there that he just showed us? That was dead time resistor range. Maximum is 500 ohms. So I don't know if that's related to this 560 that we've got on the board here. But maybe, I don't know. Maybe by going for a higher resistance, we end up with a lower dead time, sorry. Interesting. Alright, what do you reckon? Shall I try changing this? Where does that go to? Where does the other side of this resistor go to? 561. Where do you go to? Oh, I need you on. Oh, you do go to pin 5. So there is a resistance across pin 5 and 7, just like SnipeX said. SnipeX is the man. Lower resistance equals lower dead time. So if we have, okay, awesome, right, let's try it out then. All we need to do is we just need to solder a little potentiometer across that resistor. We can leave the resistor in place because we're lowering the resistance across it. So if I can find a spare little, I don't know, like something like this. Little, what's this? A 500. That could be perfect. That's a 500 ohm resistor, maybe. Is that a 500 ohm trim pot? 0 to 500 ohms. So the fact that there's a 560 ohm, what does that mean? Why is that there? Yeah, here we go, 516. Let's take a little screwdriver and turn that down. Let's vary that slightly. So that is at that's down at 0 there. So we've got 516 ohms with that down, like turned probably to max. If we turn it all the other way, we should get 0 perhaps, or it might be the other way. Okay, so it's on this middle one here. So 533 and 0. Yes, okay, awesome. So let's do this. Let's solder this on. Just very temporarily. I'm probably going to use some jumper wire real quick to solder this on. Let's cut this in half, this little piece of red wire. I'm gonna actually remove the resistor because obviously if I parallel it over the 500, we're going to start at 250, which might be too low. So let's remove the resistor real quick. Could use a 470 you took off the gate earlier. Oh, a 270. Yeah, I could try a 270 fixed, but I want control over it. You see, I want control over it, like with a potentiometer. So that's what we're going to do. We're going to just quickly remove this resistor and keep it somewhere safe. This 561. I'm going to put that up here safely by my oscilloscope so it doesn't go anywhere. There we go. And just going to put a bit of flux, maybe a bit of solder paste if I know where that is. I don't know where that is. A bit of flux. There we go. And just going to solder these wires here in. I should have done this one first. That one's in the way now. There we go. So now let's solder the other ends of these wires to the potentiometer real quick. This is just a very temporary like test. I want to get the exact resistance right, and then we can solder in a permanent resistor. There we go. Okay, there's our temporary potentiometer hooked up then, our little trim pot for finding the correct resistance for the dead time that we want to use on this amplifier. Now, I just want to make sure that we start off at 500 ohms. Make sure that we start off nice and high. Okay, so we're low at the moment, so I need to take my screwdriver and need to turn the potentiometer fully the other way. There we go. So now we should be at 516 ohms roughly. We got 514. Yep, there we go. Perfect. So now then, gentlemen, let's turn the amplifier back on and let's slowly start to decrease. Let's slowly start to decrease the resistance on our trim potentiometer and closely monitor the dead time on the gate of the MOSFET, and also closely monitor the current draw from the amplifier. So remember, the current draw is just here on the amplifier. So let's get my potentiometer here with my screwdriver. You know, this screwdriver tip actually isn't quite the right size. I'm just going to grab one that's the right size because I don't want to slip. I want to do it nice and controlled. Nice and controlled. Let's grab a screwdriver that's the right size. Here we go. There should be one in here. Yep. There we go. Perfect fit. Perfect fit. Okay. So, closely monitoring the dead time. Let's reset the dead time clear message, voltage RMS, and time duty cycle. And voltage, we're going to turn that down to just like 10.7 volts for now. Okay, here we go, gentlemen. Let's find the good dead time. So we're at 37% dead time. Let's start slowly increasing the resistance. Slowly start decreasing the resistance on this potentiometer. Watch the dead time closely. Oh, here we go. It's coming. 39%. 40%. So we're still at 1.3 amps. So we haven't changed in current draw yet. 41%, 42%, still at 1.3. We're still at 1.3. I'm gonna limit the current supply right down just in case it spikes to 2.7 amps. %, 43%. 44, 45. Oh, the current draw just went up to 1.4. See that? at 45% duty cycle, we start to increase the current draw slightly. If I go any higher, 46%. Now we're at 1.5 amps worth of current draw. So let's back it off a little bit. Okay, power supply FETs were maybe starting to heat up a little bit then, just from the... okay, interesting stuff. So if I go too high, if I go past like 45, 46, 47... Yeah, oh, there's a lot of noise actually. A lot of noise comes from the transformers when I go past that point. So this is a bit like setting bias. This is a bit like setting bias on a Class AB MOSFET amplifier. We need to go up just to be below the point where the current draw starts to increase. So we've got 1.3 amps. So it starts to go up to 1.4 when we go towards 45. So I'm going to keep her nicely at, I think, 44% duty cycle. And we're going to also try at a higher voltage as well. So with 10.7 volts worth of input, we have a nice safe spot there at 44% duty cycle. Now let's turn that back down again, all the way down to 30. So you can see that, you can see it on the screen there changing. Look at that. Yeah. So now if I increase the voltage here all the way up to, let's say, 13 volts. Okay. So we've got 13 volts now. And I'm going to start increasing the dead time again. 1.4 amps on the display this time, down low at 36%. Yeah, we can get back up to 44. Oh, then it goes to 1.5. Okay. So, yes, 44-ish% is about our sweet spot. I'm gonna go lower a bit. I'm probably gonna leave it at about 43 to be extra safe. Yeah, I'm gonna go down to about 43 to be extra safe. So that is exactly dead on 43. I'm just gonna let go of the resistor so my finger isn't implementing it. Okay, now I also want to check what the wave looks like on the output of the FET. Make sure there's not too much ringing, and also on the transformer. Okay, that looks more like what we're used to seeing. See, there's not that much ringing there just yet. And on the output of the transformer, there's not too much ringing there yet either. See, that looks fine. That's absolutely clean. That is awesome. Now, how much rail voltage did we gain from that? I'm interested to see how much rail voltage we gain. Let's turn the voltage back down to something sensible. Let's go back down to 10.7 for a sec. Just nice and low. Keep everything safe. How much rail voltage did we gain from that? So, before I touch the resistance, before I touch that potentiometer again, I just want to measure the resistance. So, that is now perfect. That is now at the point where we want to be. So, let's check the resistance across this point now. What resistance is that? And what resistor do I need to order? On the screen here, on the multimeter screen, we have 197. So I could order a 200 ohm resistor and drop it in there, and that would be pretty much perfect. Awesome. So yeah, the 270 probably wasn't actually far off. I could probably drop a 270 in there and it would actually perform better than it did with the original one in there. But I'm going to probably grab a 200 ohm from somewhere. I don't know if I have one. I might be able to have to order one. And yeah, but how much extra rail voltage did we get from that? And how much more power, maybe, can the amplifier make as a result of that? So let's first of all measure the rail voltage at 14 volts. Let's turn it back on. Let's measure the rail voltage at 14 volts. Rail voltage is here at 14 volts. So, I don't know. I'm going to go for a percentage here as well. Is important because of voltage droop. So, with that resistor in place, with 10.7 volts, we have, okay, 79 volts. So, the positive rail and the negative rail, 79.6, and the negative rail is 79.4. So we got about 79.4, 79.6. Now, if I back that down, all the way back down, 79. So remember 79. So if I back that all the way down from 79, where's my screwdriver gone? All the way back down to 0 on here. So we now should be back at 500 ohms on the resistor. Yep, back to 517 ohms. What's the rail voltage now with the original resistance in place? It's still 79 ohms, volts. Okay, so it hasn't changed our rail voltage. I thought it would. Because usually the way that these amplifiers that have a regulated power supply, the way that they regulate the rail voltage is they modify the dead time on the gate. I thought we were going to see slightly higher voltage rails, but we don't. All that we've done is we've just massively improved the efficiency of the power supply section. Voltage is due to turns on the transformer. Yes, but like I say, amplifier, if you've ever worked on an amplifier that has a regulated power supply, where it prevents the rail voltages from going too high once you start cranking up the voltage on the batteries and stuff like that, what it does is it massively limits the dead time on the power supply FETs, which prevents the rail voltages from climbing as high. So yeah, interesting one. I wonder what that's really doing. Only under load it will change, assuming unregulated supply and fixed supply volume. So H1 Nicholas, maybe you can give some insight then. So on amplifiers that run regulated power supplies, the rail voltage stays pretty much the same, and it varies the dead time on the power supply FETs to keep the rail voltage at the same level. How is it doing that then? It's not a worry going from 1.4 to 1.5. That's normal. Yeah, but I could also start to hear some ringing-y stuff. So actually, let's see what happens if we start going too high on the dead time. Let's put our multimeter probe, our oscilloscope probe, on the output of the transformer. Okay, and let's start increasing. So let's start decreasing the resistance on this resistor even more than we were. Okay, let's start going down to closer to 50% duty cycle, and let's start seeing what the wave looks like. So this is the transformer output wave. Okay, now if we start increasing this, you can see that the frequency actually gets faster, which is interesting. The frequency gets higher. The duty cycle is the same, but the frequency gets faster on the output of the transformer. Interesting. Now, as we start going higher, it starts getting sharper. Look at it getting sharper. Okay. Now, beyond a point where the current starts creeping up to 1.4, 1.5. 1.8, the current is quite increased there. It squares off. Actually, I'm down at 0 ohms now. So with it squared off at 0 ohms, the current actually only rises to 1.8. That's not so bad, hey? So that's at 0 ohms. That should be 50% duty cycle. That's actually not so bad. The amplifier's not making the strange noises it was before either when we went up that high. Let's have a look at the gate drive signal. So 37% duty cycle. When we bring it up to 50% duty cycle, that's the maximum is 47.7. So that's the chip's limit. So I think the chip's limit is 47.7. But I think do the power supply FETs start heating up? Not really. They seem to be pretty cool. If I leave it running at 50% duty cycle for a bit, what does that do? Does that start heating the power supply FETs up? And what about, especially if I increase the voltage, what happens then if I start increasing the voltage at 50% duty cycle, or like 47.7? So you see we've got a bit of ringing on there. If I increase the voltage slightly, that looks okay. We've got a bit of ringing there. So maybe that's not perfect, but, you know, I don't know. This is quite complex stuff. This is quite in-depth circuit design stuff that, you know, I've not really had great deal of experience with before. It seems to be okay. The power supply FETs aren't really getting hot. They're like just sort of lukewarm, you know, as you'd expect from running. Actually, they're not even that warm. They're just like, they're pretty much room temperature. So yeah, 1.8 amp is fine. It's got to be 50% most of the time. So yeah, I think maybe we just short over. Maybe we just short over that resistor there on the board, and we just leave it at like 47.7% duty cycle. Maybe we leave it at 47.7. At what point does the ringing go away? Nah, there's not really that much ringing. It's like a little bit. It's like if we take a look on the scope screen here, let's have a look. So this is at is this all the way at 0%? Yeah. So this is with it. So you can see a tiny bit of ringing there at the start. If I back off on the potentiometer slightly, it kind of goes away like about, there. And that is, what duty cycle is that? That is 45% duty cycle. So that's when the current draw stays at 1.3. So we've got a couple of choices then. I'll do a little bit of research into what the best thing to do is. Maybe if you guys want to join in on the chats, join the Discord server. I have a Discord server where we can discuss this in detail if you like, if you know a bit about this stuff. We have two choices. We can either, we can either leave it at 43, 44, 45% duty cycle, where the current draw at idle is 1.3 amps and the ringing is not present. Or we can whack it up to the maximum that this chip can do, 47.7% duty cycle, and we can the current draw at idle increases up to 1.8 amps, and there's a touch of ringing on the rectifiers. Yeah, which one of those should we go for? We can have a chat on the Discord. But gentlemen, I hope that you've enjoyed this. I am shattered. It is 2:30 in the morning, and I keep getting late nights because of this streaming. So I'm going to go to bed, turn my cameras off and such. Yeah, I'll see you in the Discord if you're in the Discord. If not, I'll see you on tomorrow's stream where we'll be looking at some other stuff. Let's do it. Guys, thanks for joining. Massively appreciate your support over this month, and I hope that you learned something from this stream. It's been a pleasure.